In today's lecture, you are going to watch graph theory, gate PYQs with tricks and techniques topic wise. And in case if you want all the chapters, all the concepts and PYQs with tricks and techniques, you can download Shrenik Jain Study Simplified app. Visit Discrete Mathematics course by Shrenik Jain sir. It's in English. And here you will get recorded lectures, complete coverage. Notes you will get, no need to make notes by yourself. Doubt solving group is there, and all coverage with tricks and techniques. We have three plans. Okay, one is 6-month plan, which is around 500. Then other is 1-year plan, 700, and the third is 2-year plan with 900. You can go to content section and you can check out the sample videos and you can check all the coverage. Okay, here 9 chapters are there. Complete thing is covered. Now enjoy the lecture. In today's class, we are going to solve gate PYQs on handshaking theorem and delta-delta theorem. So let us start the lecture with the very first question. First question in front of the screen. Pause the video, try, then look at my solution. Right? The question says, what is the number of vertices in an undirected connected graph with 27 edges, 6 vertices of degree 2, 3 vertices of degree 4, and remaining of degree 3? We have 4 options. Now I know when you read the question, nowhere it is written that you have to use the handshaking theorem. So always remember, whenever you see questions, there won't be direct mentioning of the theorems. It's intuitive. Looking at the data, then what we have to find, you will get the thought process. You will get the idea, oh, here we have to use the handshaking theorem. Understood? So now, let us analyze the data. What is the number of vertices? Which means n I have to find. In an undirected connected graph with 27 edges. So number of edges, E is 27. Then this is very interesting. 6 vertices of degree 2. Now I have to make the table. Number of vertices and respective degree. They are saying 6 vertices are there who is having degree 2 each. Similarly, 3 vertices are there who is having degree 4. Similarly, next we have x vertices. Remaining means x, since we do not know the total count. So we'll say that remaining should be x vertices having degree 3 each. Okay, this is given. So can you find the number of vertices in the graph? Yes, we can. How? By looking at this data, degree and edges. So handshaking theorem says summation of degree is equal to twice the number of edges. So this part is done since we know E is 27. Okay, so this is 2 into 27. Now what about this thing? Summation of degree. Some students are like 2 plus 4 plus 3. Wrong. 2 plus 4 plus 3 is not summation of degree because this data is in the form of frequency table. This is not raw data like we have seen in the class. We used to deal with the raw data. This is not raw data. Now use the statistics concept. If you want to do the summation, it would be 6 into 2 plus 3 into 4 plus x into 3. This is summation of the degree. Understood? Reason is very simple. We have 6 vertices and every vertex is having degree 2. So if you want to sum up, you will say 6 into 2. You can also do manually 2 plus 2 plus 2 plus 2 plus 2 plus 2. You will get 12, or you simply use the maths 6 into 2. Okay, 6 into 2, you will get 12. I hope you got the idea. Also concept clarity. So 12 plus 3x, that is equal to, this is what 4 and 4, 5, 54, right? Then we can say here this is 24 plus 3x, that is equal to 54. So 3x is equal to 54 minus 24, which is 30. So x is equal to 30 by 3, which is 10. When x is 10, you got this x is 10. Now they were asking a number of vertex. So add all the vertex, you will get the answer. 10 plus 3 plus 6 is 19. So option D is correct. Easy. So detailed solution is given in the notes folder. So you do not have to worry about my way of solving like a student and the proper detailed solution. Okay, so it's there in the notes folder. You do not have to make the notes. Understood? Now to the next question. Pause the video, try, then look at my solution. Tried? Now whenever you see this kind of question, I know a lot of students are like, sir, what kind of notations they are using? Is it Harvard paper or is it gate exam? It's gate exam. Things are very simple. You have to just focus on the data and what we have to find. Okay, concepts you know already. I hope this part is clear. So what is this symbol? This is KSI. You can say it as sky, okay, or psi. Generally K is silent. We say it as psi, but it is KSI. Nevertheless, you can take any symbol you want. Nevertheless, here they are saying G is equal to V comma E. V is number of vertex, E is the edge set. Okay, be a graph defined like this. So psi of G is equal to summation ID into D. What is ID and D? ID is number of vertices of degree D in G. Number of vertices of degree G in D in G. Okay. If S and T are two different trees with psi of S is equal to psi of T, then which of the following option is correct? So when they are saying mod S and mod T, what does this represent? This represents number of vertices or number of edges. So in general, this is number of vertices, not number of edges. Why? Reason is when they say S and T are two different trees, so S will have vertex. So mod S is number of vertices. Similarly, T is a tree. So mod T would be number of vertices. So in general, it is number of vertices. So they need the relation between number of vertices in S and T if this is the given condition. If you now analyze the things, it's pretty simple. When somebody is saying ID is the number of vertices of degree T in G, then you remember, oh, same kind of stuff we have done somewhat here, right? Summation D was what? Number of vertices into degree. Isn't it so? Summation of degree was number of vertices into degree. Same kind of format is going on. So this is nothing but summation degree. Oh, so handshaking theorem can be used, and we can say this psi of G is nothing but handshaking theorem summation degree, which is our 2 times number of edges in the graph. But your S and T are the graph of tree style. So if it is of the tree style like this, we have seen in the earlier chapters how tree style looks like. So whenever you draw a tree, suppose I have tree of 1, 2, 3, 4, 5 vertex, then the number of edges are 1, 2, 3, 4, 5 minus 1. 5 vertex, edges 5 minus 1. So n vertex edges would be n minus 1. Correct. So for a tree, you can say if you have n vertex, then the number of edges is n minus 1. So based on this, now our question of handshaking theorem is changed for the tree. Since the complete question is for the tree, summation of the degree is twice the number of edges, which is twice n minus 1. Isn't it so? Because both S and T are different trees. Now they are giving this condition. If this is the condition, then what is the relation in the number of vertices? We can solve here. Let me remove. Okay. So I think yes. Okay. So now if they are saying if this is the condition, then what is the relation on number of vertices? See carefully. If this thing is true, this thing is equal to this thing. So I can say this would be twice number of vertices in S would be mod S. That is equal to this would be twice number of vertices in T would be mod T. 2 getting cancelled, minus 1, then minus 1 getting cancelled, mod S is equal to mod T. So option C is correct. Very easy, isn't it so? So you have to analyze first what things are given, then you will get the intuitive idea. Oh, this is nothing but summation degree, so handshaking theorem, this is twice the number of edges. Then they are talking about the tree. So in tree, edges is what? If you have n vertices, then the edges is n minus 1. So you can modify this formula and you can say this thing is now just n minus 1. So now this condition is given and they were asking about number of vertices relation. So you used the substitution technique and you got the answer. Very simple, easy. To the final question, pause the video, try, then look at my solution. This is not final question of the class, but of the handshaking theorem. So I should not say pause the video and try, because you know the answer straight away. Which of the following statement is or are true for the undirected graph? P and Q are the statement. P statement says the number of odd degree vertex is even. Isn't it true? Why? Because this is corollary. We have proved this, that if you have a graph where odd degree counting, if you have odd degrees, then the counting of that is always even, right? So odd degree vertices in a graph, the counting, the number of them will always be even. Q is sum of degrees of all vertices is even. Is it true? Sum of the degree For all vertex it is even. Yes, why? Because as per the handshaking theorem, this value is equal to twice the number of edges, and edges belongs to the integer, so 2 times integer is always even. So yes, this is also true. So both of them are true. Option C is correct. Easy, understood. To the next question. This is a good question based on the delta delta theorem. Pause the video, try, then look at my solution. Tried? So what is happening here is we have a graph G who is having this inequality. Edge is less than equal to 3 times vertex minus 6. The minimum degree of G is defined like this, and we know in general we define as delta, small delta, like this. Capital delta is the maximum degree. As per our notation, small delta can be used. Therefore, the minimum degree of G cannot be, not possible. The smallest degree not possible. How to do it? Now you are like, sir, delta delta theorem said like this, that the minimum degree is less than equal to the average degree less than equal to the maximum degree, right? This is what the thing was. Now here we have inequality. So how to deal? How to get this stuff? Because summation degree by n is nothing but summation degree is as per handshaking theorem 2e. So 2e by n. So how to get 2e by n? Because this is not something like e is a function of e, then we can get 2e by n. But here the things are in inequality. So what to do? Therefore we have to analyze, and then we have to substitute. So it's a little bit time taking, but you will get the answer. Okay, so this is the formula through which you are getting the answer, but straight away substitution won't be possible. So we have to do little bit analysis. So this thing is saying e is less than equal to 3n minus 6, right? We are in search of what? This thing is 2e by n, right? So we are in search of 2e by n. How to get that? Multiply 2 on both the sides, so 6n minus 12, divide by n on both the side. So now this is 2e by n is less than equal to 6 minus 12 by n. Okay, so we got the idea. 2e by n is less than equal to this thing. So tell me the maximum possible value of 2e by n. The maximum possible value would be n0, no, then not defined, n1, then negative, no degree, average degree cannot be negative, then 2 would be 0 is not the maximum, since because when n is 6, then we are getting some positive degree value which is greater than 0, but the maximum degree value you will get when n is 12. When n is 12, then this is gone 1, so 6 minus 1 is 5, which means this value will be maximum 5. Okay, this value maximum would be 5, right? See carefully. Why it would be 5? When n is equal to 12, then 2e by n is less than equal to 6 minus 12 by 12, which is 6 minus 1, which is 5. So 2e by n can be maximum 5. Then it can also be like 4, 3, 2, 1, 0, but it cannot go below 0, right? This is what I am getting the idea. This is what I have analyzed. Now, they were saying minimum degree of G cannot be. If this value is 5, then 5 should be greater than equal to delta, or you can say delta should be less than equal to 5. Delta should be less than equal to 5. 6 cannot happen. Minimum degree of G cannot be 6, since if we choose this as the maximum, then we got the upper limit for delta, and once we got the upper limit for the delta, then we can say 5 is the ceiling. You cannot go beyond 5. Okay, so 6 cannot happen. Therefore option D is correct. Makes sense? Easy. Now if you might say, sir, what if we take n is equal to 4, then 6 minus 3 will happen, so this would be 3. Agreed. For that, upper limit of delta is 3. Then you, sir, then 5 and 6 is not possible. But I am saying the maximum upper limit is what? The maximum upper limit is 5 when n is 12. So if maximum upper limit is 5, you have to focus on the max, right? You have to focus on the max only. What is the maximum upper limit for the delta? It is 5. So beyond 5 it can never go. Therefore 6 it can never go. Understood? So that is the answer. Detailed solution is given. Now to the next question. Pause the video, try, then look at my solution. Tried? G is an undirected graph with n vertices and 25 edges such that each vertex of G has degree at least 3. The maximum possible value of n is. The maximum possible value of n is. Okay, so if that is the thing, again, which theorem to use? No theorem is mentioned, but see, they are saying G has degree at least 3. Minimum degree is 3. Delta is 3. Okay, so delta is 3. E is 25. N is the number of vertex, and you have to find the possible maximum value of n. No problem. So we know as per the delta theorem, the small delta is less than equal to 2e by n, right? Now this is 3, e was given as 25, n, so rearrange, n is less than equal to 2 into 25 divided by 3. So 3 ones are, okay, here it won't be like a proper answer, so we have to use the calculator. 50 divided by 3, it would be 16.66. So 16.67. So n is less than equal to 16.67. If ceiling is 16.67, which is the closest integer? 16 is the closest integer, right? See, this is 16, this is 17, and this is 16.67. So if n is less than equal to 16.67, the maximum possible integer is 16. So that is the answer. I am giving you very step-by-step explanation so that even if diploma students are watching, they should not get issue. Therefore, I am giving you very step-by-step solution. 16 is the answer. I hope this part is pretty much clear. In today's class, we are going to solve gate PYQs on Havel-Hakimi theorem and different types of graphs. So let us start the lecture with the very first question. Pause the video, try, then look at my solution. Tried? The question says, which one of the following is true for any simple connected undirected graph with more than 2 vertices? We have 4 options. Now, whenever this kind of question comes, students get stressed, they get tension. No need to worry. Why? Because in discrete mathematics, majority of the time, our trick remains same. What is the trick? The trick is take one example, then analyze the options, eliminate the wrong options. Eventually, you will land up at the right option. As simple as that. So same thing I'm going to do for this question, and then I will give you one important note. Okay, so let us see the technique. The technique is the given data is saying simple connected undirected graph, okay, with more than 2 vertices, which means vertex cannot be 2, it should be more than 2. It can be 3, 4, 5, so on and so forth. So among them, which of the following is correct? I will make one graph of 3 vertex, cycle graph. So they are talking about what? They are talking about the degrees. So I can see here degree 2, degree 2, degree 2. So no 2 vertices have the same degree. 2 vertices are having the same degree. Why you are saying no 2 vertices are having the same degree? Wrong. Option A is wrong. At least 2 vertex have same degree. Yes. At least 3 vertices have the same degree. Yes. All vertices have same degree. Yes. Take one more example. What if I take this example? Degree 3, degree 2, degree 3, degree 2. At least 2 vertices have same degree. At least 2 vertices have same degree. Makes sense. At least 3 vertices have same degree. No, we cannot find 3 vertices having the same degree here. All vertices have the same degree. Absolutely not. So option elimination says option B is correct, and that statement is nothing but the corollary of the Havel-Hakimi theorem. What is the corollary? That if you have simple connected undirected graph with more than 2 vertices, then always you will get at least 2 vertices having the same degree. Okay, so note it out. Now going to the next question, pause the video, think, then look at my solution. Try. Okay, if you have tried, then it's my turn. First of all, they are saying the degree sequence of a simple graph is the sequence of the degree of the nodes in the graph in decreasing order. Okay, we know it very well. We can see here in the option. Nevertheless, which of the following sequences cannot be the degree sequence of any graph? Cannot be the degree sequence, not a degree sequence. So now, not a degree sequence, you know very well. Havel-Hakimi theorem helps us to find whether a simple graph can be made or not, which means degree sequence exists or not. So I can use that. Indirectly, always you have to get the idea. We have to use which theorem in which question. Directly nothing would be mentioned that use Havel-Hakimi theorem and solve, or use handshaking theorem and solve. You have to analyze by yourself. understood first step. Now the problem is we have 4-degree sequence and then we have option. And I was like, to check Havel-Hakimi for every sequence will be very time taking. So do we have any tricks and techniques? Then absolutely, I got a basic concept which can be used as a trick by observing the degree sequence. See, the degree sequence is saying we have how many vertex here? 3 plus 3 plus 2, 8 vertices. Here also 3 plus 3 plus 2, 8 vertices, right? 3 plus 3 plus 2. Next also 8, next also 8. Basically, all the degree sequence are having 8 vertices. If that is the stuff, then I can say the maximum degree for all vertices for all the graph will be what? 8 minus 1, which is 7. If maximum degree is 7, this sequence is okay, this is okay, this is okay, but this is not okay. They are saying the degree is 8. Degree 8 not possible, maximum degree is 7 only. So this degree sequence is wrong and they need the wrong degree sequence. See, cannot be the degree sequence. So this cannot be the degree sequence. Okay, cannot be the degree sequence. 4 should be there in our option. 4 is not there in the option. Wrong. 4 is present, 4 is present, 4 is present. Okay. So one option is gone. Now I have to just check for the degree sequence 2 and 3, which among them cannot be our degree sequence. That would be the correct answer. So for that I have to use some technique now. Can I use any other technique? You might be thinking of summation degree should be even. Apparently summation degree is even in both these stuff. Then what to do? See, no need to check for the 1 since it's already eliminated, and no need for the first degree sequence checking since that is not present in our right options. If I say in KBC style, that option is eliminated. Okay, only we have 3 options, B, C, T. Okay, so I got no choice. Use the Havel-Hakimi theorem for this degree sequence. Okay, so first I copied, then I use the algorithm. The 6 says remove from here 1 time, 2 time, 3 time, 4 time, 5 times, 6 times, right? Do the subtraction. Now calculation is 5, 5, 5, 2, 2, 1, 2. Now is it in the decreasing style? No, so make it in the decreasing style. Now remove this 5, 1 time, 2 time, 3 time, 4 time, 5 time. Now do the calculation. 4, 4, 1, 1, 1, 1, right? 4, 4, 1, 1, 1, 1. Now is it decreasing? Yes. Remove this 4, 1 time, 2 time, 3 time, 4 time. Do the calculation. 3, 0, 0, 0, 1. Now sort 3, 1, 0, 0, 0. If you do now decrease, then you will get negative degree. Negative degree not possible. So this degree sequence not possible. They need not possible. 2 is not possible. So 2 is not possible in which option? In option D only. Therefore B, C is wrong. Option elimination. No need to check Havel-Hakimi theorem for all the degree sequence. This is how smart you can be in the GATE exam. So the correct answer is what? Option D. Understood how to solve this kind of question pretty fast? If yes, then we can move forward for the next question. And do not worry, all the detailed solution is there in the notes folder. Do not be afraid, sir, you have erased some lines, erase some calculation. Do not worry, everything is there in the notes folder. Pause the video and try this question, then look at my solution. Tried. The question says an ordered n tuple like this in the decreasing fashion is called graphic if there exists a simple indirected graph with n vertices having degree. Okay, which of the following 6 tuple is not graphic? So graphic here means I hope you got the idea. Not a degree sequence. Okay, I mean not graphic means not a degree sequence, but this kind of thing is nothing but they are saying graphic, which is our degree sequence. They are changing the term of degree sequence to a graphic. So basically what we have to find is not graphic, which is not a degree sequence. So among this, which of the following is not a degree sequence? I have told you in the class, if you have even ones, then they can cancel in the Havel-Hakimi and it's possible. What about this? This is nothing but our graph like this. Do you remember? Yes, sir, it is hexagon. See, every vertex is having degree 2 and we have 6 vertices. What about this thing? We do not know. We have to use Havel-Hakimi. So 3, 3, 3, 1, 0, 0. Remove this 3, 1 time, 2 time, 3 time. Calculation is 2, 2, 0, 0, 0. Remove this 2 1 time, 2 time. Oh, you will get the negative degree, which is not possible. So this is not possible, not a degree sequence. Yes, C is not a degree sequence. Done. No need to check for the D. Even if you use the Havel-Hakimi and check for the D, you will get it as a degree sequence. Understood? Now, let us solve gate PYQs on the graphs. Pause the video, try, then look at my solution. Tried? I do not know, a lot of students will make mistake here. They will say, sir, by looking at the option, our brain was like, yes, n into n minus 1 by 2 we have seen in the class. So that is the answer, right? Wrong. They are asking how many undirected graphs can be constructed out of the given vertex set, this thing of n vertices. How many undirected graph? They are not talking about how many number of vertices, how many number of edges. No, how many number of graphs they are asking. This is what they are asking. So to solve this kind of question, my way is again not going by the generalization. My way is using the example substitution trick to eliminate the option, apparently reach at the answer. I will do that. And if you want, you can use the probability technique to get the answer as well. But what I want to say here is there is a little bit of problem in the question. They have not mentioned about the graph has a self loop or not. See, if you say, sir, what about the multiple edges? If multiple edges are present, then infinite edges I can create, then infinite graphs can be made. So that's not my concern. My concern is about the self loop. They are not mentioning about the self loop. So even if in the exam that kind of scenario you are facing, assume this is the question without self loop, unless they are mentioning. So error in the question, I agree, they should mention about the self loop, but if nothing is mentioned, then you assume it as a simple graph and then you comment on the answer. Okay, so the correct answer is D. The reason is, if I take n is equal to 1 vertex, then number of graph only 1. This is our phi 1, only one graph can be made. So if I substitute n is 1, this is 0, n is 1, this is 2, but answer is 1, answer not 0 and 2. So this is wrong. If I substitute n is 1, 1 factorial 1, what about here 2 to the power 0, 1. So this is making sense. So I substituted n is 2. N is 2 means 2 vertex, 2 kind of graph like this or not connected graph, correct? So 2 graphs can be made. So when I substituted n is 2, so 2 factorial is 2 and this calculation is also giving me 2 only. Isn't it so? Yes. Then I failed again how to eliminate the other thing. So we have to move forward. N is equal to 3. So if you substitute n is equal to 3, then what you will get? N is equal to 3, no one is connected, phi 3, one of the graph. Now one edge graph you can make, connect this two and leave. So one edge graph, or you can connect this two. So again one edge graph, or you can connect the first and the last vertex, one edge graph. So one edge graph, 3 you can see. See carefully, this was 0 edge. Here edge is 0. These are the example where edge is 1. These are the example where edge is 2. Again that combination I have used, that first, second, third is connected, or first, second, first, third connected, second, third, first, third connected. So 2 edges, 3 graphs you can make, and edge 3 only 1 graph you can make. So total counting if you do is 1, 3, 3, 1, which is 8. So which of the following will give me 8 when n is equal to 3? 3 factorial is not 8. So C is wrong. Apparently A, B, C wrong. Only option D is right. Understood? So option elimination, substitution technique is the best thing you can do in the discrete maths to get answer pretty fast. To the next question. Pause the video, try, then look at my solution. Try it. The question says maximum number of edges in an n node undirected graph without a self loop is. Now this is very good, because they are framing without self loop. So without self loop means we are talking about the simple graph. So in simple graph, you tell me the maximum number of edges. Sir, it occurs in the k, and maximum number of edges is n into n minus 1 by 2. Straight away the answer is option B. Very easy. And if the question in future comes with a self loop, then we'll say that our answer is maximum number of edges without self loop plus maximum number of edges if you include the self loop. So every vertex will have a self loop. So n vertices will have n self loop. So n self loops, right? Now E max is n into n minus 1 by 2 plus n. So do the calculation, n into, okay, let me write in this way, n square minus n plus 2n by 2. So that is equal to n square plus n by 2. So that is n into n plus 1 by 2. So that is option D. So if they ask with self loop, then you will say without self loop plus consider all the self loop. Without self loop is n into n minus 1 by 2, and if you consider the self loops, n vertices will have n self loop, so add them, the answer comes out to be n plus 1 into n by 2. That is one more good question if in future GATE exam they ask. Try the question number 3. Maximum number of edges in an acyclic undirected graph with n vertices is what? Pause the video, think. Now you are very familiar with my technique, sir. You will use the substitution technique, obviously. So acyclic. So if I take n is equal to 3, I will get a cyclic. So when a vertex is 3, number of edges is 3, right? That's obviously the minimum and the maximum. You can say that it's 3. But if it is not cyclic, then it should stop here, right? We should eliminate this edge. Then the maximum edge is 2. So n is 3, maximum edge is n minus 1. Makes sense? When n is 3, the maximum number of edges for the acyclic, this example is acyclic since cycle is not made. This is cyclic since cycle is made. So when n is 3, I got here 3 minus 1, here 3, 3 plus 1, 6 minus 1, right? Our answer is 2. Answer is 2 only present in option A, not in the other options, so other options are wrong. Easy, understood? Very simple substitution technique. Try the next question. Pause the video, try, then look at my solution. The maximum number of edges in an bipartite graph on 12 vertices is, you know the derivation I have explained, the maximum number of edges in the bipartite, it was n square by 4, and luckily here n is 12, otherwise you can use that floor function of n by 2 into ceiling function of n by 2. That will also give you the correct answer if n was odd, but nevertheless here what is the answer? The answer is 12 square by 4. Put that into the calculator, you will get 36 as the answer. Straight away we have seen the derivation and proof in the class, so no need to repeat again. I know you know the concepts and the derivation. Try the next question. Let T be a tree with 10 vertices. The sum of the degree of all the vertices in T is, pause the video, think. Tried? So when I say tree, tree means like this, chain reaction, chain. So if I have 1, 2, 3, 4, if I have 4 vertices, the number of edges is 3. So if I have n vertices, then the number of edges is n minus 1. Already we have seen this kind of questions earlier. So now they are saying we have a tree with 10 vertices, n is equal to 10. The sum of the degree is what? Sum of the degree is twice the number of edges. Handshaking theorem. Oh, so this was a handshaking theorem question. Okay, but based on the tree graph. So here see carefully, E is what? E is n minus 1, n is 10, so 2 into 9, 18 is the answer. Yes, 18 is the answer. Try the next question. Consider a simple undirected graph of 10 vertices. If the graph is disconnected, then the maximum number of edges it can have is. Oh, so this was something new, that if the graph is disconnected, then the maximum number of edges what? Because if this thing was not there, then we know for sure that the maximum number of edges is n into n minus 1 by 2. Now they are giving a condition. The condition is if the graph is disconnected, then the maximum number of edges what? So basically among that 10 vertex, one vertex you make isolated. Okay, so one vertex you make isolated and then you check what is the answer. So if you try, then you may simply say, oh, then we have 9 vertices, and then we can say K9 answer, like n into n minus 1 by 2 is the maximum number of edges, which is 9 into 9 minus 1 by 2, which is 9 into 8 by 2, 2 1s are 2 4s are, the answer is 36. This is one way to solve. The other way to solve is, you will say, in general we know that if this condition was not there, then we know that the maximum number of edges is n into n minus 1 by 2, right? Now they are saying that if the graph is disconnected, so there would be among this vertex, there would be one vertex which I should remove. I should I should erase those edges from that isolated vertices, right? If you consider that all the vertex are connected to each other, the 10 vertices are connected to each other, this is what the thing is. But here among that 10, one is isolated, okay? And you mistakenly consider those edges also from the isolated vertices in this calculation. So I am erasing that, subtracting that edges from the isolated. Suppose I am that isolated, I will be connected to the 9 vertices, so 9 edges, right? 9 edges I have to remove. Now you do the calculation, you substitute n is 10, you will get the same answer. So 5 into 9 minus 9, 9 outside, 5 minus 1, so 9 into 4, again 36. So anyway you can solve, it's up to you, you will get the same answer. Agreed? So there was one more way to solve this question. The method 2 was simply say that 1 is isolated and 9 vertices are joined. So simply 9 into 9 minus 1 by 2 is the answer. Easy. That's it. So we are done for today. Thanks for watching the lecture. In today's class, we are going to solve gate PYQs on chromatic number. So let us start the lecture with the very first question in front of a screen. Pause the video, try, then look at my solution. Tried? The question says the minimum number of colors required to color the following graph such that no two adjacent vertices are assigned the same color, which means you have to find the chromatic number of which graph? Of this graph. How to do? Either you can use the colors green, blue, yellow, so on and so forth, or you can use the numbers 1, 2, 3. This is very effective to at the end get the answer. So I am going to use number. If I number this node as 1, which is like color of this vertex as 1, then the adjacent vertices cannot be 1. Apart from that, you can color the vertex as 1. If I do this vertex coloring as 1, then the adjacents, this is not adjacent, the adjacents cannot be 1. For this, the adjacents were this thing. So all the nodes now cannot be 1. Only 2 node, or you can say vertex, can be 1. Similarly, fill the next vertex color as, let us say, 2. If this is 2, adjacents cannot be 2, but this can be 2, then adjacents cannot be 2. Okay. If I take this as 3, then this is 3. If I take this as 4, then this is 4. 4 colors minimum it is required, and yes, the answer is C. Understood? You can use the colors like green, blue, pink. You can use that, yellow. I have no issue, but at the end you have to count how many colors you have used. So 1, 2, 3, 4. 4 is the answer. Understood? To the next question. What is the chromatic number of the following graph? Where is the graph? Oops. This is the graph. I know you have seen the solution, but try by yourself again. Tried? Okay, now it's my turn. If I color this vertex as 1, then this is the adjacent, cannot be 1. This is the adjacent, this is the adjacent, they cannot be 1, but then other players can be 1. If this is 1, then adjacents cannot be 1, but this can be 1. Then adjacents cannot be 1. Okay, but then this can be 1, right? So 1 can be filled in this 4. Isn't it so? Apart from that, can you make this as 1? No, because this would be adjacent to this vertex. Then I have color 2, 2, 2, 2, and then color 3. Minimum 3 colors are required, okay, to fill this graph. So answer is option B. To the next question. What is the chromatic number of an n vertex simple connected graph which do not contain any odd length cycle? Assume n is greater than or equal to 2. Pause the video, try, then look at my solution. Tried? Whenever this kind of question comes, you know my technique is substitution. So start with n is equal to 2. Now you will say, sir, we have two kind of graph. One is this null graph and other is this graph, simple graph. But remember, they are saying simple connected graph. If it is connected, then this is not connected, this is not allowed, this is allowed. If this is allowed, 2 colors are needed to fill this graph. So when n is 2, this is 1, we need 2 colors. We need 2 colors, not 3. So 2 options are gone. What if n is equal to 3? What will happen? 3 vertex can be joined like this. 3 vertex can be joined like this. These are the options. So if they are saying, oh, what they are saying does not contain any odd cycle, here we will have odd cycle. So if it is odd cycle, not allowed. This is allowed. So 1 2 1. Again 2. When n is 3, colors are 2. So this is wrong. Option A is correct. You can check even for the n is 4. N is 4, 2 colors are enough. 1 2 1 2, right? 2 colors are enough. So yes, the answer is option A is correct if this is the condition, that odd cycles are not allowed. Okay, odd cycle means like this, cyclic. You know it very well. In the conceptual class we have seen all the concepts, right? Now to the next question. Pause the video, try, then look at my solution. Right, the chromatic number for the following graph. Some students are like, sir, 1 2 3 4 5 6 6. No, the 6 are the vertex. They need the chromatic number. So chromatic number, now I know a lot of students will say answer is 3 or 4. Okay, the 4 ones are wrong because you are solving like this. This is wrong. Okay, always remember, you will get chromatic number when you try to fill the same colors in the alternate version. Like if 1 is here, try to find the alternate, which means alternate means leave the first adjacent vertex and try for the next. So leave this because this is adjacent, try for the next. But this is also adjacent, try for the next, adjacent, try for the next. So this should be 1. Okay, and some students, if you mark this as 1, then we are going to land up in this problem where we are getting 4 color necessity, but necessity is not 4 color. You can use 3 color as well to get the answer. I will show. If I start with 1 here, then the next vertex is this adjacent, cannot be 1, cannot be 1, cannot be 1, and the immediate next is the alternate, right? So this is 1, and if this is 1, this cannot be 1. Understood? Now you go with the next colors. Suppose this is 2, then this is 2, then finally this is 3. So 3 colors are enough. That is the answer. To the next question, pause the video, try. Tried. Very easy question again. They are asking the chromatic number of the graph. Chromatic number is the minimum number color. Okay, we know all these things, right? So what is the chromatic number of the graph? If this is 1, the adjacents cannot be 1, so give them next color. So adjacent vertices, I am giving them the next color. So if this is 2, then the adjacent vertices can be 1, and finally this is 2. Check, no 2 adjacent vertices are having the same color, so the chromatic number is just 2. Done. That's it for today. I hope you enjoyed the video. In today's class, we are going to solve gate PYQs on isomorphism and self-complementing graph. So let us start the lecture with the very first question. Pause the video, try, then look at my solution. Tried? The question is saying which of the following graph is isomorphic to this graph. So what is isomorphic? Remember, there are 2 ways. One is simple way. After playing with the structure, if this graph and the option graph is exact same, then it is isomorphic. If it is not, then it is not isomorphic. Other ways, you can use mathematical approaches. Third way is you can use tricks and techniques, but those tricks are one-way theorems, right? So which technique you used? I know you used the tricks. You started to count the vertices 1 2 3 4 5 6 7 8, and again for the options, every option you checked. What you got? Vertices is 8 for the graph and for all the options, isn't it so? Check for the option A, 1 2 3 4 5 6 7 8. Similarly the rest, you will get the vertices 8. Then you checked for the edges. What are the edges? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. If you check all the options, C and D also, what you are getting? Edges are 8. Then you check for the degree. So the degree here is 1, degree here is 4, here 2, here 2, 2, 2, 2, 1, right? Now for the option, if you check, are you getting a 4? Yes, sir, I am getting 4 here. Okay. Then you are getting 1 here, 1 here, 1 here. How come you are getting 3 ones? See, you are getting 3 ones. We have only 2 ones. So this is wrong. Then check for this. this is 4, this is 1, this is 1, this is 2, this is 2, this is 2, this is 2, this is 2. Okay, so 2 1s and 1 4 and others 2s. Makes sense, right? Option C. Now please make a note. It is not like, okay, so B is making sense, so B is the correct answer. No, this is a one-way theorem. We can only definitely say that that option is wrong, which does not satisfy the property, but we cannot comment which option is right. Okay, we can only use the option elimination technique. So now here degree 1, then we have 1 2 3. Okay, but we will not get degree 4 anywhere. See, 1 2 3, 1 2 3 here also. So 3 is not available in the degree sequence, so straight away it is wrong. Checking here, we are getting 1 1, then 2 2, this is 4, this is 2 2 2. Makes sense, right? Makes sense. Matching with the degree sequence. So which options are left? B and D options are left. Now if you check the cycle, how many cycle? 1 2 3 4 5. 5 cycle is there. Here 1 2 3 4 5. 5 cycle is there. Here 1 2 3 4. 4 cycle wrong. So option elimination is saying option B is correct. Final answer. But this technique was a time taking technique. I have a faster technique as well. Do you need the faster technique? If you need the faster technique, I will show you here. The faster technique is play with the graph. Play with graph. Okay, and see carefully the cycle, which is very easy to navigate. If I see the cycle, it is 1 2 3 4 5. 5 cycle here, no. Here 3 cycle, so wrong. Here 5 cycle, yes. Here 5 cycle, yes. Here 5 cycle, no. So this is wrong. So 2 options are gone. Now play with the graph. This graph and this graph was exactly like same until I saw this edge. Okay, see the edge. Here they are in this option C. What they are doing is they are cutting this edge and pasting here. That's what they have done. So cut and paste is not allowed. You can play with the graph, but you cannot cut and paste. So cut and paste was going on. For that reason this is wrong, and hence only one option is left. Option B is correct. Makes sense. Even if you check by the degree part, that here cut and paste happened. So degree for this vertex was 4, and nowhere I am getting the degree for the vertex 4 because they were doing cut and paste. If they had played with the graph, then the degree won't have changed. Since they cut and paste, degree got changed, and therefore method 2 was like playing with the graph and using the cycle to get the answer fast. Easy. To the next question. Pause the video, try, then look at my solution. Question says a cycle on n vertices is isomorphic to its complement. The value of n is what then? So basically the graph is cycle of n vertices Cn, and that is isomorphic, so congruent to its complement, so Cn complement. Oh, so whenever this condition is there, we can say Cn is what? Cn is self-complementing graph. Another way also we can say that if Cn is self-complementing graph, this condition should satisfy, right? It's a two-way theorem. So if that is the case, can you find the value of n? Okay, so if it is self-complementing, then the number of edges is what? N into n minus 1 by 4. This is the theorem which we have studied in the class. Now for Cn, do you remember what is the speciality about the edges? Cn is a cycle graph. So if you have 3 vertices, 3 edges. If you have 4 vertices, 4 edges. If you have 5 vertices, 5 edges. So if you have n vertices, n edges. So number of edges in the Cn graph is n, right? Because n vertices, n edges will happen. This is the basic concept which we have seen right now. N vertices, n edges. So that is equal to n into n minus 1 by 4. You can cancel it out, since actually you should not cancel, you should do it properly. Let me show you, because what if it is 0? But 0 edges is not relevant here, but still I will show you that if you, because 0 cannot happen, right? 0 edges will represent in cycle as 0 vertices, but cycle cannot have the 0 vertices. Minimum they should have 3 vertices, minimum they should have 3 edges. So 0 cannot be one of the possible answer. Okay, so this was the reason. Therefore I was like eliminate by cutting, but in actual mathematical terms you cannot cut, because what if it is 0? You cannot cut then. So rearrange. 4n is equal to multiplication of these pairs are n square minus n. Okay, rearrange again. Now 4n plus n would be 5n, that is equal to n square. So n square minus 5n equal to 0, n into n minus 5 equal to 0. So n is equal to 0 and n is equal to 5. 0 cannot be the answer, 5 is the answer. Done and dusted. Understood. Do not worry about my handwriting. Crystal clear handwriting is there in the notes folder. Proper steps are there. Okay, so this is the solution PDF from the notes folder. I hope it's clear. To the next question. A graph is self-complementary if it is isomorphic to its complement. They are giving definition of self-complementary. So for all self-complementary graph on n vertices, n is what? We have 4 options. Tried? I know a lot of students are like, obviously multiple of 4, wrong. That was the trap. Why, sir? See, if graph is self-complementing, then it's a one-way theorem for sure. We know that the number of edges is n into n minus 1 by 4, and talking about the vertices, theorem 2, they should be 4k or 4k plus 1. Or simply you can say that n should be divisible by 4 or n minus 1 should be divisible by 4. So if that is the case, now they need the idea of n, number of vertices. You are saying n should be compulsory multiple of 4. No, I told you either n should be divisible by 4 or n minus 1 should be divisible by 4. So if n is 5, so 5 not divisible by 4, agreed. But 5 minus 1 is divisible by 4. Understood? So n was odd, but it was still divisible by 4. N was not actually multiple of 4, but still it was divisible by 4 since n minus 1 was divisible by 4. Understood? So here you have to say multiple of 4 is wrong. Even 5 will satisfy the theorem. So this is wrong. Even is wrong, odd is wrong, since even divisible, odd also divisible, right? If it is greater than equal to 4. So this is also wrong. Option elimination says ABC wrong, D is correct, which makes sense. Why? Because they are saying n should be congruent to 0 mod 4. Its remainder should be 0 if divided by 4, and remainder should be 1 if divided by 4. Makes sense? Then only it is possible. See, n is equal to 6 is not allowed as per the theorem also. But if you check, when 6 divided by 4, 4 ones are 4, the remainder is 2. Remainder should not be 2. Okay, was 5 valid? N is equal to 5 valid? Yes, when k is 1, n is equal to 5 is valid. Even if you check by this statement, 4 ones are 4, remainder 1. So remainder should be 1, then it is correct. Or remainder should be 0, then it is correct. Like 4 divided by 4, remainder 0, then it is correct. So therefore option D was correct. Easy, understood. So that's it. 3 questions were there. I hope you enjoyed the class. In today's class, we are going to solve gate PYQs on these 2 topics: connectivity, Euler and Hamiltonian graph. Very important lecture. So let us start the lecture with the very first question. Let G be an arbitrary graph with n vertices and k connected components. If a vertex is removed from the graph, the number of components in the resulting graph must necessarily lie between which option is correct? We have different range: k to n, k minus 1 to k plus 1, k minus 1 to n minus 1, k plus 1 to n minus k. Pause the video and try, then look at my solution. I hope you have tried and you have said option B. That is what I expected. That is absolutely wrong. Also explained in our conceptual class. Do you remember? Very big discussion I have made on this. If you remember, it's good. If you do not remember, no problem. Let me explain again. See, a lot of students take this example and they say that this graph is having connected component 1. Remove the vertex V. Resultant graph is like this. Still number of component is 1. But if you have graph like this, k is 1 here. Now remove V. Sir, number of connected component increased by 1. See here, k is equal to 2. Yes, increased by 1. So maximum is increased by 1, minimum is like this, and they are like, yes, maximum increased by 1. Earlier it was k, now it is k plus 1. If you remove a vertex, this is maximum. This is what they are thinking. This is their thought process. But if you have watched my conceptual lecture, then you remember maximum number of component occurs in the star graph. Yes, I have given that question. Is it necessary that k should only increase by +1 if you remove a vertex? No. For many examples, this is what it will be, but for special case like star graph, this won't be the maximum. The maximum would be n-1. Okay, let me explain by the example. Suppose I have a star graph like this. Okay, if I remove the center vertex v, what will happen? Sir, the resultant would look like this. Earlier k is 1, only one connected component. Now there are 6 components, got increased by 5. Actually, if you see, got increased by n-1. Since earlier we had 7 vertices, now we have 6 vertices, right? So k is 6, k value is n-1, that is the maximum. Not k plus 1, the resultant is not k plus 1, check, is it k plus 1? No. So I will say, for this example, which of the following says maximum? N is saying 7, no, 7 is not the answer, 6 is the answer. K plus 1 is 1 plus 1, 2, 2 is not the answer. N minus 1, yes, 7 minus 1, 6 is the answer. N minus k, 7 minus 6, that is 1, no, that is not the answer. Done. Option elimination. Counter example. This is what you have to think. Now some student may have doubts, sir, why minimum k minus 1? Why not minimum k, like here, removing a vertex v? Previously k was 1, now also k is 1. So after that also k is the connected component. Why here minimum is k minus 1? I have example for that also, do not worry. See, when I say minimum is k minus 1, this happens when you are dealing with disconnected graph. See, earlier I have a disconnected graph like this. So number of connected component is 2. Remove the vertex v. If you remove this vertex v, then k is 1, only one connected component. So your minimum is k minus 1. Earlier it was 2, now it is 2 minus 1. So this minimum happens only for this isolate vertex disconnected graph. Okay, remember, minimum will happen in isolated vertex disconnected graph, maximum will happen in the star graph. So this is your conclusion. If a vertex is removed, minimum k minus 1 component, maximum n-1 components. Okay, examples are given. These are the special cases of minima and maxima. Very beautiful question. So if you have studied the conceptual lecture, if you have revised, you can solve this kind of tough questions. Question number 2 in front of a screen. Pause the video and try. Discrete mathematics feels tough because there is no direct formula. It's always analysis of the concept, remembering the lecture, applying those special cases, having counter example. This is what discrete mathematics questions feels like. Therefore, unlike the engineering mathematics, this feels little tough. Okay. Tried the question. The question says, let G is V comma E set be a directed graph. This is a directed graph question. And V is set of vertices, E be the set of edges. Which one of the following graph has the same strongly connected component as G? So by default they are saying that this G graph is strongly connected. Now same strongly connected feeling you will get in which of the following option? G1, G2, G3, G4. So if that is the case, then by looking at the option, G1 is V comma E1, where E1 is U comma V not belonging to the E set. Edges which are present in G should, like, see, edges present in G is edges, that same edges not present in the E1, not present in the G1. This is what the example is saying. Those same edges of G you should not consider here. Okay, so we have to analyze. Option B is saying G2 is V comma E2, where E2 is same edges that as per the E set. Oh, same vertices, same edges. If this is strongly connected, then same graph. Yes, it's like isomorphism. This is also strongly connected. Done. Option B is correct. In exam, you have to be that quick. If the options are little less tough, read, feels someone is correct, done, no need to check for the rest. But being a teacher, I will explain each and every option, why the other options are incorrect. But in exam, I have told you, option A you read, you didn't get any feeling, next. Option B you read, you got the feeling both of them are same graph. It's like isomorphism. So if G is strongly connected, then G2 is similar to G. So it's also strongly connected. No need to check for the rest. But why option A, C, D is wrong? A is wrong because if this is my graph G, this is my G graph having set of vertices and edges. See, vertices are AB, edges are AB and BA. Here order matters since we are dealing with the directed graph. So what we can observe here is this G graph is strongly connected, because the definition says for strongly connected there should be a path from x to y and y to x. This is what our definition said. And here also you can check that A to B we have a path, and then B to A also we have a path. It's not or, it's and here. So yes, this is right example. But if you are saying G1 is a graph where you have vertices same, so these are the vertices, but edge set is not same as your G edge set, original graph edge set. So if edges are not same, I have to remove them from the G graph, remove them. This is your G1 graph. But this G1 graph is not strongly connected since there is no path from A to B and B to A. Therefore, this option is wrong. This is one counter example. Understood? Original graph was strongly connected, but if you remove the edges from the graph and you say our E1 is the new set of edges where those edges does not belong to the original graph. So remove this and then see it's not strongly connected. Option A is wrong. Option B is isomorphism. So done. Why option C is incorrect? Option C says G3 is a graph, vertices is same, changing the edges. Edges are such, U comma V is mapped. There is a path of length less than equal to 2 from U to V in G. So if you take this example, you will say yes, this thing is correct. C should be correct, right? Because length here is 2. Number of edges is length. So length here is 2. So this makes sense, sir, less than equal to 2. But if you take this example, then it failed. This doesn't work for every example. That's what you have to verify. Is it working for every example? Here it will work for every example. If G is strongly connected, then this player is isomorphic. So this is also strongly connected. Both of them will work for every case, therefore every time true. This don't work every time. Check this example. Here you will say that A to B, this graph is a strongly connected graph because we have a path from A to B and also from B to A. Agreed? And you take any two vertex pair, always you will get x to y and y to x path. But length 1, 2, 3. Length here 1, 2, 3, 4. Not less than equal to 2. Still it is happening. So this is incorrect. Option C is incorrect. Why option D is incorrect? G4 is, now they are changing the vertices, not the edges. Edges of G and G4 are same, vertices are different. They are saying V4 is the set of vertices in G which are not isolated. Okay. They are saying not isolated, then only strongly connected. But I am taking this example. This is my G graph. This is my G graph and this is strongly connected. Okay. Now they are saying V4 is set of vertices in G which are not isolated. So remove this. There is no graph. If no graph, then how strongly connected? So this failed. This is incorrect. Counter example. I hope every counter example is clear. And in exam how to solve, I have explained. Read all the option. Whichever feels easy, investigate. If it is correct, good. Not, then invest time and analyze by the counter example. Okay. To the question number 3. In a connected graph, a bridge is an edge whose removal disconnects the graph. Which one of the following statement is true? We have 4 options. Pause the video, try, then look at my solution. Tried. So here they are saying in a connected graph, very important. A bridge, you remember a bridge? Edge connectivity, yes. So if you remove an edge, just one edge, so it's vertex, not vertex, it's cut edge. So basically here they are talking about cut edge because an edge is one edge. So one edge removal disconnects the graph. disconnects the graph, then which of the following statement is true? A tree has no bridges. Wrong. Every tree is having a bridge, and every edge is a bridge. You take any example of tree, if you remove this edge, resultant is like this, so that edge was a bridge. If you remove this edge, that edge is a bridge. So every edge is a bridge. And you are saying a tree has no bridge? Absolutely nonsense, incorrect. A bridge cannot be a part of simple cycle. If you have a simple cycle like this, they are saying a bridge cannot be a part of the simple cycle. Yes, in simple cycle, if you remove this thing, if you remove this edge, still it is connected, it is not disconnected. If you remove this, still it is connected, it is not disconnected. So any edge is not behaving as bridge, so a bridge cannot be a part of simple cycle. Makes sense? Done. I won't check C and D in the exam, but as a teacher I will check here. Why option C and D is incorrect? Check. C is saying every edge of a click with size greater than equal to 3 is a bridge, where they are saying click is an complete subgraph of a graph. Okay, so they are saying if size is greater than equal to 3, then every edge will behave as a bridge. No, because if you are saying click is any complete subgraph of a graph, if I have this graph, okay, and you are taking subgraph of this, a triangle, so triangle is a cycle, cycle will never have a bridge, and you are saying every edge is a bridge. Incorrect. Simple counter example. Incorrect. Option D incorrect. Why? A graph with bridges cannot have a cycle. Who said? Who said a graph with bridges cannot have a cycle? Take this example. In this example, this edge is a bridge, because if you remove this triangle and isolation, you get two components, right? So this graph has a bridge and it is also having a cycle. You are saying a graph having a bridge cannot have a cycle. No, this is wrong. But this is one of the important trap. If you study, if you read all the options, then you will wonder B is correct or D is correct. If it is MSQ, some student might say B and D, because if there is a cycle, then cycle graphs are never having bridge. So yes, option D also makes sense. They are not saying cycle graph bridge or not. They are saying if bridge is there, then not a cycle. So here bridge is there, still a cycle. This is the question. If the question was cycle graph never has bridge, makes sense. But that was our statement B. Statement B and statement D are totally different, so you have to be very cautious in MSQ. For now it is MCQ, so you can use these tricks and techniques, whichever is easy option. If you feel it's correct, done. No need to check others. Try the question number 4. Now the question says, so which of the following graph has an Eulerian circuit? We have 4 options. Pause the video, try, then look at my solution. Tried? You will say, sir, very easy question, option A is correct. That's what I expected. Absolutely incorrect. Sir, but in the class you have told Kn graphs are always a Eulerian graph if it is connected and all the vertices having the degree even. Yes, I have told, I agree. Then sir, same thing? No, these two are not same. Check. In the option, are they saying the graph is connected always? No sir, they are just saying K regular graph where K is an even graph. Then I have this example. See. Tell me, this graph, is it K regular graph? Yes. Why it is K regular graph? Because everywhere the vertex is having degree even. Yes, 2, 2, 2. So even degree still, it's not Eulerian. Why not Eulerian? There is a disconnect here, and disconnect graphs issue will create how I will cover the rest edges, and since I cannot cover all the edges, it's not Eulerian circuit. Understood why option A is incorrect. If they just modify the option and say any connected K regular graph where K is even, then yes, Eulerian. But here connected was missing, so very critical. So option A is incorrect. Option B, a complete graph of 90 vertices is definitely not Eulerian. Reason is, in a complete graph, all the vertices having the degree n minus 1. So here 90 minus 1 is 89, so degree is odd. Whenever you get odd degree, those graphs are never Eulerian. Now come C and D. If C is correct, D is incorrect. If C is incorrect, D is correct. So you have to check the complement of a cycle on 25 vertices. Is it Eulerian? Here you have to work. There is no such standard formula. So here you have to work. You have to understand what is a complement, already explained in the conceptual class. This is the answer, but how it came, I will explain, because at the end of the day, complement of a cycle is a connected graph, and then we have to check the degrees. If degrees are even, then Eulerian. Not even, not Eulerian. Whenever connected is there, then it's a two-way theorem. Here it was not connected graph, so you cannot say two-way theorem. Complete graphs are by default connected graphs. Here cycle graph is by default connected graph. So here, if I see carefully, the complement of a cycle on 25 vertices. Okay. So complement of cycle, if you want to find, it is Kn minus Cn. This is your complement of the cycle. Definition we already know. Already we have studied in the conceptual class. Still I am doing a revision so that you understand why option C is correct. When I draw C3 graph, this is the graph. C dash will be vertices same, and then Kn edges you have to remove. So this is also present in Kn. So remove all the edges. This is the thing. What is the degree of every vertex? It is 0. C4 is this graph. Kn graph would look like this. So the uncommon edges are the edges in the C4 dash. So that is our answer. Similarly, C5. C5 is this cycle. Kn K5 looks like this. This is our K5 graph. The uncommon will be our C dash 5. Remember my simple trick to draw the graphs fast? If yes, then check. Degree here 1, 1, 1, 1. Every vertex is having degree 1. Degree here 2. So if you make formula now, 3 vertices degree 3 minus 3. 4 vertices degree 4 minus 3. 5 vertices degree 5 minus 3. So if n vertices degree is n minus 3. Here we have 25 vertices. So C dash will have how many degree? 25 minus 3, 22. All the vertices having even degree plus connected. So Eulerian. So option C is correct. Understood? Very beautiful question, because connected, not connected. Very critical words. Since connected was not present, option wrong. If present, option was correct. So you have to be very cautious in this kind of question. Try the next question, question number 5. G is a simple connected, undirected graph. Some vertices of G are of odd degree and a node V to G, and make it adjacent to each odd degree vertex of G. Then the resultant graph is sure to be what? Pause the video, try, then look at my solution. You can verify by the example. Suppose I have some vertices of odd degree, some vertices even degree, and a node V to G, and make it adjacent to odd degree vertex, adjacent to the odd degree vertex, adjacent, adjacent, adjacent. So if you make that, then all the vertex will get a +1 increase in their degree value. So they will be even now. And now I can see all the vertices are having even degree plus connected. I should definitely say Eulerian graph, no need to check other. Even if you check, all the options will be wrong. Easy, understood. To the question number 6. Let G be a complete undirected graph on 6 vertices. If vertices of G are labeled, then the number of distinct cycle of length 4 in G is equal to what? Pause the video, try, then look at my solution. So just previous lecture, last slide, do you remember labeled, unlabeled? So here it's labeled, therefore answer is not 1. And then they are saying we have 6 vertices, complete graph. So complete graph, every vertex connected to every other vertices, like that. So we have 6 vertices. From that 6 vertices, you have to find the number of distinct cycle of length 4. So length 4 cycle will be generated by the 4 vertices. From 6 vertices, choose 4 vertices, and you need cycle. So number of cycles, distinct cycles, unordered count, that is n minus 1 factorial by 2. Remember the formula. So n here is 4, since you are choosing 4 vertices and you need cycle from that. So 4 minus 1 factorial, since circular permutation, and divide by 2 to avoid the clockwise and anti-clockwise nature, since it doesn't matter here. And that's all. This is the final answer. 6C4 is 6C2, which is 6 into 5 by 2 into 3 factorial, which is 3 into 2 factorial, or you can say 3 into 2 into 1 upon 2. Cancels, 2 1s are 2 3s are. Final answer is 15 into 3, which is equal to 45. So option C is correct. Easy. So this thing is already explained conceptually in the previous lecture. So if you have seen the conceptual lecture, then only this class is easy. I am again saying, if you are just solving the PYQ, 100% you cannot solve any PYQ, because traps here. By books, if you go, special cases are not covered, minimum and maximum. You have to think, you have to research, you have to refer more and more books. Then only you will get this idea that minimum happens in the isolation and maximum happens in the star graph. If you have seen my lecture, then also you get the idea. So it's a good question. Second question was slightly easy. Since isomorphic graphs, then definitely strongly connected, or you can develop counter examples. No issue in that. It will take time. If it was MSQ, then definitely it will take time, but you can solve the question. This was again easy question, but if it was MSQ, might be tough. Student might get trapped in B and D, but easy to eliminate A and C. In D, you have to be cautious that there can be a graph which will have a bridge but not a cycle. Okay. And then we have seen this very, very critical and a trap question, because just a connected word was missed and you guys are like option A, option A. So, connected present, then okay, but not connected given, so therefore option A was incorrect. B was definitely incorrect very fast, and C we have to verify. Degree was n-3 for this complement cycle, and we have seen the logic behind it. If I straight away give the formula, you will say, sir, how? So I just gave you the style, algorithm style, and we arrived at n-3. Question number 5 was easy, no problem. Connected plus you are increasing the odd degree value by 1, so even degree every 1, therefore Euler. This was also easy because we have learned conceptually in the previous lecture. Number of distinct cycles, if you need, then it is n-1 factorial by 2. And since we had 6 vertices, we have to make a length of 4, choose combination and your cycle. This is the final answer. Thanks for watching the lecture. In today's class, we are going to solve GATE PYQs on planar graphs. A lot of questions are asked in GATE exam based on this topic. Let us see all the questions now one by one. First question in front of your screen. Pause the video, try, then look at my solution. Tried. The question says, let G be a simple connected planar graph with 13 vertices and 19 edges. Then the number of faces in the planar embedding of the graph is what? If you see the keyword carefully, simple connected planar graph, I guess this was enough. For the indication, we have to use the Euler's formula. What is the Euler's formula? Whenever you have connected planar graph, the Euler's formula is number of region is equal to number of edges minus number of vertices plus 2. Here they are saying 13 vertices, okay. 19 edges, okay. Then the number of faces in the planar. Tell me what is the answer? 19 minus 13 is 6. 6 plus 2 is 8. So the correct answer is option B, done and dusted. Okay. So simple connected, multi-connected, pseudo-connected, every time this is the formula. Easy. Try the next question. Which one of the following graphs is not planar? We have 4 graphs. One of them is correct. Pause the video, try, then look at my solution. Tried. Okay, now it's my turn to solve the question. First of all, among this graph, which one is easy to handle? Even if you go step by step, even if you start with the graph one. So basically here we have hexagon. So hexagon we have like this. And then, okay, this edge can be drawn. This edge I will take from here, but this edge how I will draw? If I go like this, overlap will happen. If I go via this route, again overlap will happen. If I go via this route, again overlap will happen. So overlap will happen because of this edge, and therefore it is not planar. Done. The answer is G1 is not planar. As simple as that. I hope this part is pretty much clear. This is how you can solve the question. But since my task is not to just give you solution, to also verify other options why these graphs are planar. So see carefully, G2 is planar because you can draw the graph without making the edges overlap. This line can be taken from outside, see. So no edges are overlapped, therefore planar graph. This is also planar. Keep this edge, take the other edge from outside. Okay, so the resultant graph looks like this. Planar graph, no edges overlap. This we have seen in the class itself. This is not a non-planar graph, since this is not a K5. If you join this line, then it becomes K5, then it becomes non-planar, correct? But this thing is a planar. We have checked in the class also, so check the class notes. Homework. G1 is the correct answer. To the next question. Pause the video, try, then look at my solution. Tried. The question says, let G be the non-planar graph with minimum possible number of edges. Oh, they are saying a non-planar graph. We know non-planar graphs are K5 and K33. Ǩurtonovsky's first graph, Ǩurtonovsky's second graph, right? They are talking about minimum possible number of edges. That happens where? That happens here. Minimum vertices happens where? Happens here. Class notes, do you remember? If you remember, you will say K33 graph is the answer. In the K33 graph, number of edges is 3 into 3, 9. Number of vertices is 3 plus 3, 6. Number of vertices 6 and number of edges 9. They needed the minimum possible number of edges. So K33 is the answer, and that is nothing but option B, right? Very fast. If you have studied the lecture, if you have revised the notes, you can solve very fast. These questions are not tough. All the questions, okay, one question you will get toughness, but majority question is easy. Try the next question. Pause the video, try, then look at my solution. Tried. Question says K4 and Q3 are the graphs. Which of the following statement is true about this graph? K4 is planar, Q3 is not. Both of them are planar. Q3 is planar, K4 is not. Both of them are not planar. If you have seen the lecture, you will say, sir, K4 is always planar. K4 is planar and therefore not a planar. K4 not planar, options are wrong. Talking about Q3, Q3 is also planar. Okay, so Q3 is also planar. The answer is option B. But do not worry, if you do not know the lecture notes, then we can prove in the exam. Check, you can draw this graph such that no edges are overlapping. So planar. You can also draw this graph so that no edges overlap. See, we have a square backside and this front side square, make it small and punch it to the backside. So make it small and punch it to the backside. This is how it looks. And since the edges are connected like this to the backside, so make edges connected to the backside. See, all the edges are drawn where edges are not overlapping. Therefore, it is a planar graph. Option B is correct. So if you know the notes, good. If you do not know the notes, you can make graph and you can prove it. Okay. To the next question. Pause the video, try, then look at my solution. Tried. Question says G be a simple undirected planar graph of 10 vertices and 15 edges. G is a connected graph. The number of bounded faces. Bounded faces. Do you remember? Do you remember planar graph give us unbounded and bounded faces? See, suppose I have this planar graph. This is region 1, outside is region 2. This outside region is unbounded region. And this is bounded region. If you take one more graph, this is R1, this is R2, R3. So outside is unbounded, inside you are getting bounded. So every time we will get only one unbounded region and others will be bounded. You take any graph, you take this graph. Region 1, region 2, region 3, region 4. So region 4 is unbounded, other regions are bounded. So only one region is unbounded, that is the outside region. So if they are asking about the bounded region, so from the answer we'll subtract 1. That's all we'll do. Okay. Since here the formula remains same. They are talking about connected graph. Connected graph and it is simple undirected planar graph. If both things are there, connected plus any planar graph. Any planar graph. It can be simple also, multi also, pseudo also. I will repeat every time since you should not get confused. If this is the thing, then one-way theorem of Euler says number of region is equal to number of edges minus number of vertices plus 2. Here edges are 15, vertices are 10. So do the calculation. 5 plus 2 is 7. But this 7 is not the answer. If I was the gate examiner, I have the very dangerous mind. I will keep one of the option as 7. And I know a lot of students will mark 7. That is incorrect. 7 is incorrect since 7 has one unbounded region plus 6 bounded region. So the correct answer is 6 bounded region. Option D is correct. Makes sense? Easy. To the next question. This is moderate level. Pause the video, try, then look at my solution. Tried. The question says, let delta denote the minimum degree of a vertex in a graph for all planar graphs on n vertices with degree greater than equal to 3. Which one of the following is true? We have 4 options. Option A, in any planar embedding, the number of faces is at least n by 2 plus 2. Option B says it's less than n by 2 plus 2. Option C is saying there is a planar embedding in which the number of faces is less than n by 2 plus 2. And option D is saying number of faces is at most n by delta plus 1. So which one is correct? I know what you are doing. Sir, planar graphs, then we can use the Euler's formula. R is equal to number of edges minus number of vertices plus 2. Absolutely wrong. Why? Because plus 2 is used only when you have planar plus connected graph. In this question, anywhere they are talking about connected graph? Check. Yes, they are talking about planar graphs, but nothing about connected graph. Then why you are using this formula? Wrong. You have to use general formula. R is E minus N plus K plus 1. This is the formula, general formula we are going to use for this question. And surprisingly, you made the mistake. A lot of books, PYQ book solution also made the same mistake. They use this formula, and even though using the wrong formula and all these things, they got the correct answer. You might also have gotten the correct answer, option A, but that was not the right solution. I will tell you what is the right solution. Okay, so now first thing first, we know which formula we are going to use. Euler's formula for any planar graph is R is equal to E minus N plus K plus 1. Now see, the given data is saying minimum degree is greater than equal to 3. And we also know delta theorem. Delta is less than equal to average degree. What is average degree? 2e by n. So delta is less than equal to 2e by n. Compare this inequality with this inequality. Compare and make your conclusion of the inequality. So given data was delta is greater than equal to 3. As per our theorem, delta is less than equal to 2e by n. So can I say 2e by n is greater than equal to delta, and delta is greater than equal to 3. So just connect here. Delta is greater than equal to 3. This is what you will get. 2e by n is greater than equal to delta from here. And then delta is greater than equal to 3. This is what you will get. So if this is the thing, can I say 2e by n, since it is greater than delta and delta is greater than equal to 3, then 2e by n is also greater than equal to 3. Simple inequalities. Aptitude we have studied, simple inequalities. So 2e by n is greater than equal to 3. Rearrange and you will get the edges answer now. Edges is greater than equal to 3n by 2. Edges is greater than equal to 3n by 2. Okay. Now this data and this equation will combine to arrive at the final conclusion. So in the next step, Euler's formula for general scenario. And now we have concluded E is greater than equal to 3n by 2. Now please make a note, if you combine these two expressions, you have to be very cautious in the analysis, that if E is equal to 3n by 2, then there is no issue. Substitute E is 3n by 2. But what is happening here is E is greater than equal to 3n by 2. And if E is greater, if E increases, then definitely R will also increase. Because R is equal to this thing, right? So R will also increase. Therefore R is greater than equal to, if you substitute E is 3n by 2. Easy understood? If understood, now do the calculation. Combine this two. It would be 3n minus 2n by 2, which is n by 2, and then we have plus k plus 1. Okay, so number of faces is at least n by 2 plus k plus 1. That should be the option, but that is not present, which means you can see plus 2, plus 2, plus 2. So indirectly they are saying substitute k is equal to 1. So R is greater than equal to n by 2 plus, if I substitute k is 1, then k plus 1 would be 2. Okay, so substitute k is 1, I am getting this thing. If you have disconnected components, surely r value will be greater. And what this is saying is, this is the minimum region which you can expect, n by 2 plus 2. If it is connected, this is the minimum. If it is disconnected, more values will come. But r minimum is n by 2 plus 2. That's what it is saying. Now you can have connected also, disconnected also, anything, but minimum will be this thing only. Understood? So therefore option A is correct. In any planar embedding, the number of faces is this thing. Okay, it should not be like there is a planar, because any planar I am saying simple graph, multi-graph, pseudo-graph, for every graph it works, not for some specific, every graph. Okay, so option A is correct. Easy, understood. To the next question. Pause the video, try, then look at my solution. Tried. Let G be a connected planar graph with 10 vertices. If the number of edges on each face is 3, then the number of edges in G is, again, a moderate level question. Because they are saying connected and planar graph. Now you can happily say R is equal to E minus N plus 2. Number of vertices is 10, so this is 10. If the number of edges on each face is 3, this thing is given, then the number of edges is what? So instead of R given directly, indirectly they are giving R. If the number of edges on each face is 3, do you remember derivation, class lecture, last slides, derivation I have explained. During derivation I have told you that if 3 edges are used to make a region, then R is equal to, you will get maximum pieces, right? Maximum regions. R is equal to what? 2e by 3. 2 because every edge is shared with 2 regions. So 2e by 3. In derivation I have explained. So same thing. So R is 2e by 3. Since here also they are saying each face is 3. Each face is 3. Which means number of edges in each face made by 3 edges. Yes. Which means they are talking about triangle. So this is the R value, maximum they are trying to cover the region. So R is 2e by 3. Substitute R is 2e by 3. E we do not know, 10 plus 2. So now I can say this is minus 8 and take this E here. So 2e minus this thing, that is equal to minus 8. Simplify 2e minus 3 by 3, that is equal to minus 8. So minus E is equal to minus 8 into 3. So E is equal to 24. That is the answer. Easy. So if you have done the derivation, if you have done the lectures, this is easy. Otherwise it is tough since R is indirectly given. To the next question. And do not worry, solution is there in the notes folder, proper way, where I have written also from class. Do you remember the maximum region? It happens when you use 3 edges to make a region. And so R is 2e by 3. Why 2 also? Because every edge is shared by the 2 regions. So twice. Question number 8. Pause the video, try, then look at my solution. It's easy question. In an undirected connected planar graph, there are 8 vertices, 5 faces, number of edges is simple, direct formula. N is given, R is given, E is asked. And also they are saying connected planar. So Euler's formula can be used. No brainer. We have solved very tough questions. This is super easy. To the next question, final question. Tough question. Pause the video, try, then look at my solution. Tried. It's MSQ. The following simple undirected graph is referred to as Peterson's graph. I know you will say it should be E, but gate examiner is like son of Peter. So jokes apart, actually it should be E. That is gate examiner's mistake. Nevertheless, which of the following statement is or are true? So one option can be true, more than one can be true. So tell me, what is the answer? The correct answer is A, B, C. D is wrong. I know some key pointers you know already from the class notes. Chromatic number is 3, Hamiltonian path is there. This thing is tough, and this thing is also easy to figure it out. This is incorrect. Why? So let us focus on A, B, D first, then we'll focus on C, because C option was actually very tough. But if you see my solution, it's very easy. Let us go step by step. Why option A and B is correct? Because from the class notes we know that is not the solution. The solution is the chromatic number figure looks like this. If this is 1, adjacents cannot be 1, so I am making it 2. Okay, then I am taking this node coloring 1, so adjacent cannot be 1. So I am making this as 3, Why? Because its adjacent is 2 already, so I cannot mark here 2, right? And why here 3? Because its adjacent is already 2, so this cannot be 2, so we have to mark it as 3, third color. So this is done. Now I can mark this node as 1. Okay, this node as 1. Who are the adjacent? Already colored, already colored. This one I am making 3. Why? Because adjacent is 2. So it cannot be 2, it cannot be 1, since adjacent are 2 and 1. Okay, so it has to be the third color. And final node would be 1 because adjacents are 2 and 3. And this is how we have colored all the vertices using the 3 colors, and therefore the chromatic number of the graph is 3. Easy. In the class we have studied, same thing I have repeated. Hamiltonian path class we have studied, started here, traveled, come here, go here, go here, go here, go here. So all the vertices are covered, start and end is different. Therefore Hamiltonian path is there, Hamiltonian cycle is not there. Okay, so A and B options are definitely correct. But this graph and this graph, are they isomorphic? Are they isomorphic? Then you know tricks only for finding not isomorphic. Not isomorphic. What was the trick? If the graphs are isomorphic, then properties should be satisfied. What are the properties? Number of vertices should be same, number of edges should be same, degree sequence should be same, and cycles should be same. Okay, if this is true, then this is true, and if this becomes false, definitely we say not isomorphic. So we only guaranteed about not isomorphic using the tricks. We do not know whether it is isomorphic or not if this passes, and that's what happened in this question. All the property passed here, and now we are confused. We do not know about isomorphism. Then check here, number of vertices same, number of edges same, degree sequence same, everyone is 3, cycle also same. So if right hand side is same, then we do not know about the left hand side, isomorphic or not. Those students who do not know properties and tricks correctly, they by fluke said, oh, if right hand side is true, left hand side is also true, and let me mark C. That is wrong approach, that is wrong conclusion. If right hand side is true, left hand side can be true or false. In the class we have seen this kind of logic many times, and therefore we failed here to use tricks and techniques. I have always told you tricks can fail. In the lectures also I have told you. So whenever tricks fails, what to do? Conclusion is check manually. So check manually. Now we'll do manual checking. See how we'll do manual checking. Playing with the graphs. I'll try to prove these two are same. Now please make a note, I am not going to sit here and try to adjust the wiring such that it comes out like this. This playing style I am not going to do, because even if I do in this lecture, but this cannot be done in the actual GATE exam, then you will blame me, sir, your methods can't be used in the GATE exam, then what's the point of learning? I know that review. For that reason, I'm not going to use that style. You will get this kind of solution in some website, books, videos, but I'm not going to use that since it is not feasible in the GATE exam. So what is feasible in the GATE exam? That method I can show. So that method is, I'm going to play via unique style. See, this node is 1 connected to this node 2, 3, 4 via the edges. So draw it. It will look like a tree. 2, 3, 4. Now this 2 is connected to, let us say, this node 5 and node 6 via this edges. 2 is connected to 5 and 6 via this edges. Okay. Then I can see 3 is connected to, let me take this 7 and 8. 3 is connected to 7 and 8. Then 4 is connected to 9 and 10. 4 is connected to 9 and 10. Also there are some edges left. 6 is connected to 9 and 8. So 6 is connected to 9 and 6 is connected to 8. Then 7 is connected to 9 and 5. 7 is connected to 9 and 7 is connected to 5. Then this 10 is connected to 8 and 5. 10 is connected to 8 and 10 is connected to 5. I hope this graph is pretty much clear. Okay. This graph is pretty much clear. If this graph is clear, this kind of graph can you see here in H? If yes, then they are isomorphic, otherwise they are not. Very simple tree style I am making. So this is one. I know it's kind of a messy, but see, this is the simplest solution you can get. 3, 4. So 1 is connected to 2, 3, 4. Then 3, okay, let me start with 2. 2 is further connected to 5 and 6. So 2 is connected to 5 and 6. 3 is connected to 7 and 8. 3 is connected to 7 and 8. 4 is connected to 9 and 10. 4 is connected to 9 and 10. Again, here also I can say this 5 has 7 to 10 edge. 5 has 7 to 10 edge. This 7 is having, okay, let me take in this way. This 9 is having edge to 7 and 6. 9 is having edge to 7 and 6. And finally, 8 is having edge to 6 and 8. 6 and 8 is having edge to 6 and 10. Oops. Okay. So 8 is having edge to 6 and 10. So this is 6, this is 10. Can you get the same feeling that in the middle leaf, you will see a vertex having connection to the first and the last. So in the middle leaf, there is a node having connection to the first and the last. Yes. Then in the last leaf, it has connection to the second and the first node. So in the last we have connection to the second and the first. And this are done. 8 and 9 is done. Now talking about this, first leaf has a node connection to second and third. First leaf has a connection to second and third. So yes, this graph is exactly matching. Now if I remove the numbers, you will find this graph are exactly same. That's what isomorphism is. Graph should look exactly same. So yes, this graph looks exactly same. If you just do a proper mirroring and arrangement, you will find these two graphs are exactly same, and therefore they are isomorphic. Understood? So this was the simplest solution which you can get. A, B, C is correct. D is wrong. Reason is very simple. See, they are saying the size of the largest independent set of the given graph is 3. What is independent set? Independent set means this vertex should not, if there is a set of vertices, then all these vertices A, B, C, so on, they should not be neighbor of each other. So if I consider this 1, okay, as A, then neighbors are this 2, 2, 2. So I have to erase. This is not the neighbor, so I can consider this B. So A is considered, B is considered. Neighbors you have to eliminate. These are the neighbors, these are the neighbors, eliminated. Can I consider this C? Yes, I can consider C. Eliminate the neighbors, all the others are eliminated, and this is final D. So this is final D. So independent set, we are having 4 vertices, so the size is 4. If size is 4, then size 3 is incorrect, so D is incorrect. Finally, A, B, C is correct. I hope this part is pretty much clear. So it was easy to identify A, B, D, little tough to identify C, because this is what the style you have to follow. Tricks here fail. Easy, understood? And that's it for today. Lot of questions were there in the planar graph and we have solved it all. Thanks for watching the lecture. In today's class, we are going to solve gate PYQs on adjacency matrix and MIS. Let us start the lecture with the very first question. Pause the video, try, then look at my solution. Tried? Now, whenever you see this kind of question, the length is very big, so you feel the question is very tough. But no, questions are easy. I will give you techniques how to make it more easy. Let us read the question. Question says G is a graph which is made from vertex and edge set, be an undirected, unweighted, connected graph. The diameter of G is defined like this. And you know, this is nothing but definition of diameter. Already we have studied in the previous lectures, right? Further, they are saying let M be the adjacency matrix of G. Define graph G2 on the same set of vertices with adjacency matrix n, where n elements are 1 or 0. 1 when you have mij greater than 0 or pij greater than 0. What is P? P is M square matrix. And this element is 0 otherwise. So which of the following statement is true? There is some inequalities between the diameter of G and diameter of G2. So basically we have to find the diameter of G and diameter of G2 from this data. Then we can comment on this inequalities. Understood? So my thesis, my approach, my technique is, when I read this question, I try to segregate into two parts. One part is about the G, other part is about G2, and finally we have to find a diameter of G and G2. So let us see what all the things are given about the G. Graph G is made from V and E as vertex set and edge set. This is undirected, unweighted, connected graph. So very important, you should not take example of disconnected graph. You should take only example of the connected graph. And then that's it. They are saying this vertex and edges are used to make the matrix M, that is adjacency matrix of the graph G. And from all this given data, you have to find the diameter of G. This is my first thing. Then the second thing is how to find the diameter of G2. For that, all this thesis is given. So what this data says, this data says graph 2 is again made from vertices and edges, but vertices are of same set, edges are different. Why edges are different? Because nothing about edges is mentioned, but they are mentioning about adjacency matrix N. So it is not M. If it was M, then vertex edge set same. It is a different new matrix, adjacency matrix N. So if it has a new adjacency matrix, obviously the edges connections are different here. And how they are connected? Given like this. N matrix elements are 1 and 0 respectively. Here the conditions are given. So you analyze and you figure it out. What is that N matrix? Then you get the idea about how the graph will look like. And then you find your diameter. Find diameter of G2. So little effort will be needed in this second section. And once you get diameter of G and diameter of G2, finally you will get the answer very easy. So this is how you have to break the question. Once you know the breaking of the question, now we can investigate step by step. So the very first step would be talking about the G graph. So the G graph, I'm taking one example like this. Is it connected? Is it undirected, unweighted graph? Yes. So it's a valid example. You have to always check whether you are taking valid examples or not as per the given data. Now if you see carefully, what is the adjacency matrix here? Adjacency matrix is M, which is made from vertices cross vertices. So A, B, C are the vertices here and here. If I won't explain the concept, but I still feel I should explain, so I will give you one more revision on it. So adjacency matrices are made such that if edges are present between the vertices, then 1. If edges are not present between the vertices, 0. So here tell me A to A, can you see edge? No self loop, 0. Similarly B to B, no self loop, 0. C to C, no self loop, 0. So diagonal elements are done. This is how fast you can develop the adjacency matrix. Then A to B, if we see edge, 1. A to C, no edge, 0. So this thing will be copied here. No need to again investigate since it is undirected graph. Aij is Aj. Do you remember the lecture? If yes, then finally these two elements are left. So what about BC? Do we have edge? Yes. So 1. And if this is 1, this is 1. Aij is Aj. Done. Adjacency matrix is ready. That fast. Now we can say from this technique, G graph we have drawn, M matrix we have made. Now we can comment on the diameter of G. So what is diameter of G? Diameter of this graph should be the, I should write the definition first, otherwise you will feel tough. So diameter of G is max of mean. So what is max of mean? So max of mean means mean here is, if you have vertex 1 comma vertex 2, so you have to take the minimum distance, shortest distance between any two vertex. So if you see carefully, the technique which I have explained you is to find the diameter, always think of the diagonals or the very opposite or very far vertices, that only will give you the diameter, since diameter is maximum shortest distance, right? So if I take this vertex A and vertex C, they are very far apart, and if that is the case, you can see travel like this, so two edges are needed. So here minimum distance, shorter distance is 2, and that is our maximum in every pair of vertex combination. You can try. AB will be 1, BC will be 1, only AC is 2. So 1 comma 1 comma 2, which is the maximum value? 2. So that is the answer. That was my trick. Trick was take the far vertices or take the diagonal vertices. You will get the maximum value of all the shortest distances. Okay. And we got the diameter. Diameter is 2. You can see here. We can move forward and we can comment on G2 now. Now G2 direct graph is not there. See, G2 we do not know the direct graph, but what we know is there is a relation between the adjacency matrix N and M matrix. How? See, here they are saying Nij element is 1 if your M matrix elements are greater than 0 or P matrix element is greater than 0 where P is M square. So now I need M square first. Then only I will say P matrix is ready. So what is M square? M is this. Can you find M square? Students are like, yes, M into M. That is time taking. In GATE exam, we do not have that much time. So in a GATE exam, you have to be smart enough. You have to be cautious enough that you save time. So how to save time? M square you can develop by using the concept of number of walk of length 2. So this was our graph. Tell me A to A. If I want to go, then number of walks of length 2, how many walks are there? Only 1. A to B, B to A, only 1. So 1. What about AB? AB you will never get walk of length 2. Okay, so 0. A to C, yes, we'll get A to B, B to C. So 2 length walk, only 1 such style, so 1. B to A, now this is copy paste. This values will be copied here, no extra effort. Okay. Talking about B to B. B to B, there are 2 ways. B to A, then A to B. Walk of length 2. And then we have B to C, C to B. Walk of length 2. So 2 such walks we have. So 2 here. B to C, no such walk, 0. So this 0 will be copied here. And finally C to C. C to C, walk of length 2. C to B, B to C, 2. Right. 2 means length 2. Number of walks is 1. Only C to B, B to C, only such one style of walk is there of length 2. So 1 is the answer. Makes sense? So this how fast you can generate your M square matrix. Once your M and M square matrix are ready, now use the definition and try to fill your N matrix. So your N matrix will look like all of them are 1. Why? Because this thing says if you want to fill your first position, which is what? First position is N11. N11. So N11, it is 1 if either M11 is having greater than 0 element or M square is having greater than 0 element. So yes, M square is having greater than 0 element, therefore N11 is 1. Similarly for the next, N12 is 1 if either here you see greater than 0 or here you see greater than 0. So we can see here greater than 0, therefore this is 1. Similarly for every position check. For 1, 3, here it is greater than 0, therefore 1. For 2, 1, here it is greater than 0, so 1. So everywhere you will find here greater than 0, here greater than 0. For this position, here greater than 0. For this, here greater than 0. For this position, here greater than 0. So for every position, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay. So either this was having greater than 0 or this was having greater than 0. So everyone was having greater than 0. And therefore I can say that N is equal to this matrix. Once this matrix is ready, then we can comment on the G2 graph, because this matrix is what? This is adjacency matrix of the G2 graph. So ABC vertices, we can say how these ABC vertices are connected. A to A, there is a self loop, B to B there is a self loop, C to C there is a self loop. So all the self loops first. Then they are saying A is connected to B, A is connected to C. So A is connected to B, A is connected to C. So this is done, this is done, this is done. Also B is connected to C. If B is connected to C, obviously C is connected to B. So this is done and self loop was done. So now every edges are covered. This is how your graph looks like. Every vertex is connected to every other vertex, plus there are self loops. This is what the matrix is saying. Now if you see this matrix, now you tell me the diameter of G2. If you take A and C far apart, still they are connected by a one edge. So diameter is 1. A to B diameter 1, B to C diameter 1. So you take any pair of vertices, the shorter distance is 1, and since everyone is 1, then the maximum is 1 only. Therefore the diameter is here is 1 only. So the diameter of G2 is 1 only. So finally we got diameter of G2, diameter of G. How we generated, I hope now it is very crystal clear. Whenever you see the question, try to break into simple steps. Once you break that into simple step, then investigate step by step, taking example and then moving forward. Okay, so since we have now diameter of G2 and diameter of G, we can use the options now and do the option elimination. Diameter of G was 2, diameter of G2 was 1. Can I say 2 is less than 1? Obviously no, so straight away wrong. Here ceiling function of 2 by 2 1. 1 is less than 1. No, 1 is not less than 1. 1 is less than equal to 1. Okay, 1 equal to 1. Okay, but you cannot say 1 is less than 1. So wrong. 1 less than 1 wrong. So this was 1 less than equal to 2 by 2. So 1 is less than equal to ceiling function of 1, which is 1. So yes, makes sense. Makes sense doesn't mean it's the right option key. We have to also check for the last option. Diameter of G2, which was 1, that is equal to diameter of G. No, it was 2. So this is absolutely wrong. Only one option makes sense. Option C is correct. Easy, understood how to solve this kind of question. Let us go to the next question. Consider a simple undirected unweighted graph with at least 3 vertices. If A is the adjacency matrix of the graph, then the number of 3 triangles in the graph is given by trace of what? Straight away you will remember, sir, class notes. Straight away you will mark. What is the answer? Yes, trace of A cube by 6. So why trace of A cube by 6? Because that triangle is repeated 6 times. How 6 times? This vertex A will travel clockwise and cover this triangle, will travel anti-clockwise and cover the triangle. So this triangle, let me take 1. This triangle 1 is covered by A twice, clockwise and anti-clockwise, right? So clockwise and anti-clockwise. Similarly, this triangle 1 is covered by B also. Same style, clockwise and anti-clockwise. So twice. C also twice, check. Clockwise and anti-clockwise, so twice. So twice plus twice plus twice is 6 times. So this triangle was repeated 6 times, and therefore you can say trace of A cube by 6. I hope you remember trace of A cube by 6, class notes, everything was explained. So it's just the revision which I have explained. ABC, every vertex covers this triangle exactly 2 times. And therefore this thing is happening. Since you are dealing with what? You are dealing with the number of 3 cycles, which means walk of length 3. So if you start with C, this is my first length, then this is my second, and this is my third. So clockwise 1 time, anti-clockwise 1 time, all the vertex will do the same thing. So this triangle will repeat 6 times. Therefore we are doing divide by 6. Makes sense, easy. Okay, so question number 3. Pause the video, try, then look at my solution. Again you will say, sir, very easy, class notes, straight away we can comment. But since I am teacher, I will explain all the options. But in the exam, once you get the correct option, click and move forward. So which of the following property hold for the adjacency matrix A of a simple undirected unweighted graph having n vertices? The diagonal entries of A square are the degrees of the vertices of the graph. Do you remember how beautifully I have explained this thing? That yes, since you are saying A square means what? Square represents number of walks of length 2. Okay, length 2. So if I am here, how will I get length 2? I go to next vertex and then come again. So that kind of nature is nothing but giving us significance of one edge. See, I'm going to that vertex and coming back. So this is nothing but saying that one edge is present between me and that vertex. Similarly, if you see now the diagonal entries will be like AA. So this vertex to next and coming back. So that is what AA walk of length 2 means. Similarly, B to B, B to B, and so on and so forth for everything. Suppose here the value is 2. What does this indicate? A to A, I have 2 such walks. One walk is from, let us say, A to some vertex 1 and then coming back, then A to some vertex 2 and coming back. This means there are 2 edges. There are 2 edges from this vertex, there are 2 edges. So degree is 2. In short, it talks about degree of the vertex. So yes, degree is 2. Explain in the class, till I am giving you the reasoning for the simple reason that you get a revision. But I hope this part is pretty much clear. And you can also verify with the example. If you do not remember the class notes, that A with walk length 2 is actually nothing but number of edges, and that is nothing but degree of the vertex. But if you do not remember, then you can any day take examples and verify. Suppose I am taking this graph x, y and z. Okay, so as per the question, simple undirected unweighted graph with n vertices. So I am taking that. So once you took this example, now find a square, and that only you have to find the diagonal entries, since you have to verify the diagonal. Okay, diagonal entries of a square. So actually no need for all these things. Just for the complete solution, I am giving this in the notes, but in the exam, no need to find the other entries, only focus on the diagonal entries. So for the diagonal entries, tell me x to x, number of walks of length 2. X to y, y to z, x to z, z to x. So these are our 2 such walks, right? X to y, y to x, length 2, first kind of walk. X to z, z to x, length 2, second kind of walk. So 2 number of walks. Then y to y only 1 I will get, y to x, x to y, length 2, only one such style. Z to z only 1 I will get, since z to x, x to z, only one such style. Now these are nothing but degrees of respective vertices. See, x vertex degrees 2, 2 edges, y vertex degrees 1, 1 edge, z vertex degrees 1, 1 edge. Yes. So the diagonal entries of a square are the degrees of vertices of the graph. Absolutely true, done and dusted. No need to check for B, C, D. But why B, C, D is wrong? Let us investigate. B says if the graph is connected, then none of the entries of e to the power n minus 1 plus in can be 0. Take the same example. Let us re-verify. Number of vertices is 3. So this calculation would be a to the power 3 minus 1 plus I3, which is a square plus I3. A square have we found already. So now we have to find complete thing. Okay. So yes, we have found completely. Then plus we have to do I3. I3 is identity matrix. Matrices you have studied. So now matrix addition will result me 2 plus 1 is 3. But 0 plus 0 is 0. If 0 plus 0 is 0, and you are saying that if the graph is connected, then none of the entries can be 0. We are taking graph connected. This is a logic question. P implies Q. So if P is true, Q should be true. So if graph is connected, graph connected, true. Then your Q should be true. None of the entries can be 0. But here Q is false. We got entry 0. So if we got false, true implies false is false. Therefore, this is false. This is wrong. Understood? Using logic. So using logic will solve, so that you understand our techniques, how to deal with such statements. Because in exam, different kind of questions can be framed, since different kind of analysis and theorems and conclusions can be derived from different graphs. You cannot remember all such theorems and analysis. You should have techniques such that we can investigate every theorems and questions. So this is one of the technique. We use the logic style. P implies Q. So if P true, Q true. Sometimes we are going to use different style, like this question. Statement C said what? If the sum of all the elements of A is at most 2 to the power n minus 1, then the graph must be acyclical. This is what the statement is saying. If P, then Q. So what is P here? Sum of all the elements of the A matrix is at most 2 to the power n minus 1. If this is P, then Q should be what? Q must be acyclic. So they are saying P implies Q should be true. If that is the case, then if Q is false, what will happen to P? P will also be false. This thing you already know in isomorphism, one-way theorem. Okay, in a lot of theorems we have used this technique only. If you remember, same technique I am going to use. What I am going to check here is, if I make a Q false, then P is false. If yes, then this is correct statement. But if P becomes true, then this is false statement. Okay, let us also understand this with the help of logic table. The table says if Q is false and P, if it is true, true implies false is false. But if P is false, then false implies false is true. So when you fix your Q, the result depends on the P. If P is true, result false. If P is false, result true. This is how the table is saying. And this technique I am using for this statement. I will make Q false and then I will investigate P. P true, option false. P false, option true. As simple as that. Understood my approach? If understood my approach, let us now apply that, taking one example. So Q false means what? Q here is must be a acyclic. So if Q is acyclic, opposite will be cyclic. So I am taking one cyclic example like this. Now your concern might be, sir, why disconnected graph? Because in connected graph, many a times you will get the statements correct. So you have to always find counter examples such that this statement will be tested very heatedly. So disconnected is such examples. So if I take a disconnected graph, this is also a cyclic. You can see a cycle here. And now let us investigate about the P. P was if sum of all the elements of A is at most 2 to the power n minus 1. This is P. So for that I have to create A matrix. Very easy. Adjacency matrix, how to create? Take nodes 1, 2, 3, 4, 5 here and here. Once you take the nodes, now check edge is present or not. No self loop, so primary diagonal element 0. You can create this very fast. Okay, primary diagonal elements 0. Then from 1 we can see only 2 edge, 1 to 2, 1 to 3, so 1 to 2, 1 to 3, others are 0, same copy here. From 2 I can see 2 edges, right? So 2 to 1, 2 to 3, 2 to 1 is already done, 2 to 3 present, right? Others are 0, so copy here. From 3 to 2, 3 to 1 is already done, so 3 to 4, 5 is not present, 0, copy here. Then 4 to 5, 1, so copy here. Matrix is ready. Once your A matrix is ready, then they need summation of all the elements. So start to add everything like this, or be smart, add the row 1 elements, add the row 2 elements, add the row 3 elements, add the row 4 elements, add the row 5 elements, then add this completely. You will get 8. Okay, this also you can do. 2 methods to add the elements of the matrix. But once you get A, then you will say summation value is 8. But as per the statement, summation is at most, which means less than equal to 2n minus 1, less than equal to 2 times n minus 1. Is it true? N was 1, 2, 3, 4, 5. N was 5. So 5 minus 1 is 4. 4 into 2 is 8. So yes, this is true. Oh, this means Q false, but P is true. Result would be, if P true, result is false. So this statement is false. That is our conclusion. Understood how this technique works? If yes, try for the statement D. If there is at least a 1 in each of a row and column, then the graph must be connected. Again, this if then one-way condition. Okay, so P implies Q. So P implies Q, again same technique. Q false, then P should be false, then only this statement is true. If P is true, then this conclusion is false. Same technique. So Q false I will take. What is Q here? The Q says the graph must be connected. If Q is talking about connected, then Q false will talk about disconnected. So I'm taking disconnected. So once you are taking disconnected, the previous example is good to go. So the disconnected, we already know the A matrix. Now they are saying if there is at least, so what is the P? P statement is at least one, like a 1, at least one entry is 1 in each of A's rows and column. Is it true? Yes. In this row and in this column, at least one entry is 1. Okay, here also. Row 2, column 2, at least one entry is 1. Everywhere you see. Okay. row 3, column 3, at least one entry is 1. Row 4, column 4, yes, here also, here also. So every row and column is having at least one of the entry as 1, and therefore this P is true. So what happens? Q false, P true, result is false. Understood? Very simple approach. This is the approach which you have to keep in mind. Okay? And C and D, therefore it is incorrect. In exam, no need to check, but I've given all the conclusions and steps so that if in future exams this kind of questions come, you know the approach, you know the technique, which examples as counter example you have to take, and how to analyze this kind of statements. Okay? To the question number 4. Pause the video, try, then look at my solution. Tried? Let A be the adjacency matrix of simple undirected graph G. Suppose A is its own inverse. Which of the following statement is always true? Only one option would be correct. So here, a lot of students take counter examples and then they say, sir, no such graph exists. So D is correct. That is wrong. That is wrong. When you take counter example, try to analyze that. Is there any example where it will overcome the recent challenges? If yes, then move forward in the iterations of the example. Okay. So the correct answer is actually B. Why? Let us investigate. So the very first step is to analyze the data. The data is saying A matrix is its own inverse. So A is equal to A inverse, pre-multiply A on both the side. Then you will say, as per the matrices, A into A is A square, A into A inverse is identity matrix. So A square is identity matrix. From this data, can you generate a graph? Obviously, since identity matrix is there, primary diagonal elements are 1, other elements are 0. So we can create it, sir, no issue. If yes, then you might have tried with 1 vertex, 2 vertex, 3 vertex, and you failed to get such graphs. One of the example, I tried with 3 vertices A, B, C. So what is A square actually telling? All these entries are number of walks of length 2. So A to A, you will get a walk of length 2 and only one such walk. So I can see A to B connection should be there. Then only I can say there is a walk of length 2, A to B, then B to A. Walk of length 2, and only one such walk I am getting. Okay, so this is a valid. Don't try to connect A to C. If you try to connect A to C, then this entry is wrong. Then you have 2 such walks. A to C, C to A is also there. A to B, B to A also there. So 2 such walks are there. So you cannot connect A and C vertices. Only A, B. Then B to B, yes. B to A to B, length 2, number of walks 1. Then C to C, how you will generate then? C to C, number of walks 1, length 2. How you will generate? Will you connect this 2? Then you will say C to B, B to C, length 2, number of walk 1. Correct, sir. If you do this, then B will change. Then B cannot be 1. B has to be 2. Then for B, I have 2 such walks of length 2. BC, CB, and then BA, AB. So I cannot create example, sir. Option D is trying to say me, there is no such graph, sir. There is no such graph. But you understood the challenge. The challenge is for C, I need one more vertex. If I connect with that, that would be very fruitful. So I thought of going forward in this iteration. Let me create one more vertex D and connect with that. Is it matching now? Matrix and this graph, is it matching? Do we have such graph? So yes, we have such graph. Graph exists which satisfies this condition A square is I. Check here. A to A, only one such walk of length 2. Yes, A to B, B to A. Only one walk of length 2. B to B, only one walk of length 2. B to A to B. Yes. C to C, only one walk of length 2. C to D, D to C. Yes. D to D, only one walk of length 2. D to C, C to D. Makes sense? Makes sense. This graph is valid. If this graph exists, then option D is wrong. Option D is wrong. Option A and C is also wrong, since option A talks about cycle. Those were not cycle. And C talks about complete graph. Those graph was not complete graph. Right? So option elimination says B option is correct. Very beautiful question. But now you will say, sir, what is perfect matching? We have concept. Matching means a set of edges such that no edges share common vertex. Remember, matching means what? You will have a set. That set will have what? Vertices or edges? Focus on edges. Okay, that set will have edges. But suppose if that set has edge, only one edge in the set, then no issue. That is always matching. But if it has two edge, then may or may not be matching. How to check, sir, it is matching or not? Edge 1, if vertices are AB. Edge 2 should not have vertex AB. It can have CD. But if it has BC, no. Since common vertex should not be there. That's what they are saying. A set of edges such that no two edges share a common vertex. If that is the case, then only we say matching. If we find any edge sharing common vertex, not matching. What is a perfect matching then? This thing plus one more criteria. All the vertices are covered. Okay. So a perfect matching means a matching that covers all the vertices, that is every vertex is incident to exactly one edge. Okay, no need to see for this. In example we'll see and we'll come back to this definition again, but for now simply we can say it should be matching plus edges should be such that it covers all the vertices. Okay, now let us see some example. 1 2 3 4 5, this is my graph. Can I say M set which is 1, 2, 3, 4. So 1, 2 means edge, 3, 4 is again edge. So it is a set of edges. Can I say this thing as matching? Yes, because both the edges are not sharing common vertex, and therefore we can say yes, it is matching. But can I say it is perfect matching? No, since one of the vertex is missed. Therefore it is not a perfect matching. What if I say M is equal to 1, 2, 2, 3? Again set of edges, but common vertex is present, therefore not matching. If it is not matching, no point of talking about perfect matching. Definitely it won't be a perfect matching since it is not matching, right? Talking about the third, we have a graph 1 connected to 2, 2 connected to 3, 3 connected to 4, and this is a set made from edges. Can I say it is matching? Check. 1 to 2 first edge, 3 to 4 is the second edge, no common vertices between the edges, and therefore yes, it's matching. But can I say it is perfect matching? You will say, sir, perfect matching means all the vertices should be covered and it should be a matching. Therefore, sir, it is a perfect matching. Answer is no. Answer is no, because perfect matching also has one more condition. I told you this thing while dealing with the example. I will explain. Every vertex is incident to exactly one edge, which indirectly means the degree of all the vertices should be 1. Okay, so it should be matching plus all the vertices covered plus the degree of all the vertices should be 1. I hope this thing is clear. If this thing is clear, then you will say this 2 and 3 is not having degree 1, therefore this is not a perfect matching. As simple as that. So now I hope you understood the concept of matching and perfect matching. So you can also see some conclusions in perfect matching with n vertices. What you will observe is n must be even. Then only it will happen degree 1 and they are connected, like one edge AB, other would be CD, but no connection between them, and then next would be EF. So obviously one edge will create 2 vertex, therefore every edge create 2 vertex, therefore n must be even. There are n by 2 edges, and very obvious, if I have 4 vertex, then one edge this, one edge this. This cannot be done since degree 2, this cannot be done since degree 2. Therefore, if 4 vertex is there, then 2 edges are created. N by 2 edges will always be created. And every vertex has the degree 1, very obvious. So this is what the proper definition of perfect matching looks like. If understood this thing, and now I guess you have understood this example. This is definitely a perfect matching example. Okay, to the question number 5. Pause the video, try, then look at my solution. Tried? What is the size of the smallest MIS, maximal independent set of a chain of a 9 nodes? Tried? A lot of students they say 5. That is wrong. In the class I have explained that MIS is not maximum independent set. Okay, both of them are different. Maximal independent set is different, maximum independent set is different. Do not get confused. And if you remember the lecture, if you have revised it, then you know very well that we can take example and we can work on it. So I'm taking example. This is my 9 nodes like a chain, okay, and I can create MIS, various MIS I can create. One of them is alternate players from 1. So 1, 3, 5, 7, 9. Okay, if I take 1, 3, 5, 7, 9, this is set of independent vertices, because if you try to add any other vertex, you will find neighbors among 1, 3, 5, 7, 9. So this means no other vertex can be added to this set. Therefore, this is maximal independent set. This is what the definition of maximal independent set said. And finally, I'm going to say the size is 5. We can see 5, but they need the smallest MIS. They need the smallest, not the largest size. If they asked about the largest size, definitely 5 is the largest. Okay, but the question was not about the largest. Then I thought about starting with 2, then 4, then 6, then 8. This is size 4. So some students are like, size 4 is the answer. No, because they thought of this, and they also thought of going from 1 to 4 and then taking 7 and then taking 9. Okay, so they were thinking like that also. If I take 1, 4, 7, 9, is it a valid maximal independent set? I cannot add 2 since it is neighbor of 1, cannot add 3 since it is neighbor of 4, 5 is neighbor of 4, 6 is neighbor of 7, 8 is neighbor of 7 and 9. Okay, 1, 4, 7, 9 are independent, and yes, this is also one of the set, but again I am getting 4. So what I thought was, in this the issue is this 1 and this 9 cannot cover right and left neighbors. Therefore, why to take this for the smallest? Let me start with 2. So left, right, I won't consider. Then I will take this 5. Left, right neighbors I won't consider. Then I will take 8. Left, right neighbor I won't consider. So 2, 6, 8. Okay, oh, not 2, 6, 2, 5, 8. 2, 5, 8 were such vertices which had the left and the right hands. And left and the right hands are nothing but giving them the neighbor, so avoiding them. 2 having 1, 3, avoid. 5 having 4, 6, avoid. 8 having 7, 9, avoid. So this 2, 5, 8 are independent, plus no other vertex can be added into this set since any other vertex will behave as the neighbor. Therefore, this is MIS, and this is the smallest MIS for this example. So the answer is 3. Understood? Made sense? So this is how you can solve the question. And going to the question number 6, the minimum number of colors that is sufficient to vertex color any planar graph is. Straight away class notes. What is the answer? 4. Why? Because K5 is non-planar, therefore chromatic number cannot be 5, and K4 is the planar, that is the highest complete graph can be said as a planar, and therefore he will require the maximum chromatic number 4, and other players K3, K2, K1 can be dealt with less than 4. So if you take any graph now, any planar graph, maximum 4 colors are enough to deal with. Okay, so they are asking minimum number of colors that is sufficient to vertex color any planar graph. It is 4. Okay, 4 is the upper limit. If you need more, you can use, but if you are in search of minimum number of colors, that is nothing but chromatic number. Okay, so sufficient chromatic number is nothing but the upper limit of chromatic number. So upper limit of chromatic number is 4 for any planar graph. Therefore, the statement was our planar graphs are 4 colorable since the upper limit, the sufficient colors are 4. No need for giving 5, 6. If you want, you can, but that would be unnecessary color. If you need the minimum color chromatic number, then upper limit is 4. Understood? Question number 6. Question number 7. Pause the video, try, then look at my solution. Again, easy question. If you have seen the class notes, you can solve directly. Let G be a simple finite undirected graph with the set of vertices. Delta is the maximum degree, n is the colors. Color the vertices of G using following greedy strategy. So coloring using the greedy algorithm. So if you remember greedy algorithm, so this is what they are giving us. Which of the following is or are true? This is MSQ. One or more options can be correct. So tell me what is the correct answer. This process results in proper vertex coloring, definitely, since greedy algorithm was actually algorithm for vertex coloring, so it gives the proper vertex coloring, no issue. The number of color used is at most delta plus 1. Yes, since chromatic number is greater than equal to delta plus 1, right? So the chromatic number says the minimum colors to be used, and greedy means he will try to use the minimum only. He will try. He will not always use the minimum. He will try to use the minimum. So the upper bound is delta plus 1. Make sense? Makes sense. Upper bound is delta plus 1. The number of colors used is at most delta. Wrong. Wrong. Why wrong? Because it was Brooks' theorem, which works for connected, but at the end of the day, this is not a specific question for a connected only, and starting with a delta greater than equal to 3. So this is not a conditioned graph. This is simple, finite, undirected graph, a general statement. So Brooks' theorem cannot be used here. The number of colors used in is equal to the chromatic number. Definitely no. We have seen example in the class note as well. So only A and B is correct. Other options are wrong. Make sense? Easy? If easy, then let us go to the question number 8. Pause the video, try, then look at my solution. Again, MSQ question, so you have to check every option. The chromatic number of a graph is the minimum number of colors used in a proper coloring of the graph. G be any graph with n vertices, chromatic number k. Which of the following is or are true? Tried. Okay, so it's my turn to solve the question. I will give you all the methods how to deal with this kind of question. First of all, we have a graph G. This graph is any graph with n vertices and chromatic number k. Generally we use chromatic number symbol as chi, but here they are using k, no problem. So which of the following statement is true? Statement A says G contains a complete subgraph with k vertices. K is what? Chromatic number. So you are trying to say chromatic number is equal to complete subgraph of k vertices. Complete subgraph of chromatic number vertices. Are you trying to say me equal for some chromatic number? We never got theorems for chromatic number is equal to this thing. We always got chromatic number is greater than equal to something, less than equal to something, but never got equal to something. So by that simple observation, I can say saying equal for any graph. This is not some specific graph condition. For any graph you are talking, equal never comes. For that simple observation, I will say option is incorrect. But I know some student took examples. Some examples are like correct. But if you remember, you got correct for some example. If you want incorrect, remember my class notes that chromatic number generally comes out to be equal to your click number. But if you want chromatic number is not equal to the click number, which is nothing but greater than click number, take the pentagon example. If you remember the class notes, by that simple class note example, you can prove this statement false. Let me show you. So where you got correct statements in this first two examples, and where it will fail in this third example. Okay, let me prove. Suppose I have only one vertex, one color is needed, chromatic number 1, number of vertex 1, but they are not interested in the number of vertex of the graph. They are interested in complete subgraph. From that graph, take the complete Kn version as a subgraph, okay, and on that check whether it is k vertices. They are saying G contains a complete subgraph always with k vertices. They are saying this thing. So okay, so if I take this example, this graph itself is a phi 1 as complete subgraph in itself. This graph is in itself a subgraph. So subgraph of phi 1, and definitely this phi 1 is nothing but phi k. This subgraph vertex is equal to the chromatic number. Check, chromatic number was 1. So subgraph vertex, it's very important, subgraph vertex should be equal to chromatic number. I repeat, subgraph vertex, not the complete vertex of the graph. Subgraph vertex is equal to the chromatic number. So yes, subgraph vertex 1, chromatic number is also 1. For this example, chromatic number 2, number of vertices of the graph 2, subgraph is also this graph only, so that is nothing but k2. So can I say vertices in the subgraph is equal to chromatic number? Check. Yes. So you are like, yes, sir, this statement is true. Subgraph vertex, that to complete subgraph vertex is equal, the number of vertices in that is equal to chromatic number. Yes, sir. But if I take pentagon, number of vertices 5, chromatic number needed 3. So talk about the subgraph. Sir, the complete subgraph here is K2. K2. We cannot have K3 since no triangle. But K2 has 2 vertices only, but our chromatic number is 3, so K2 is not equal to Kk. Therefore, this is false. No need to dive into such details in the exam since you know the theorems. Straight away you can eliminate option A. Now talking about B, C and D. Step by step we'll see. Why B is true? G contains an independent set of size at least n by k. Makes sense. They are talking about an independent set. Contains an, which means at least one. At least one. Okay. G contains an independent set. There exists at least one set of size at least n by k. And definitely, do you remember n by k, number of vertex by chromatic number? Yes, sir. Beta is greater than equal to ceiling function of n by k. So what was beta? Beta was independence number. What is independence number? Number of vertices in the largest MIS. Largest MIS. What is MIS? Maximal independent set. Can I say that is nothing but independent set? So we have at least one independent set. Yes. So this is true. So just see. Contains independent set of size at least n by k. Your brain should be like, n by k we have seen, that is nothing but beta. Beta is greater than equal to n by k. So what is beta? Independence number made from largest MIS, and MIS is nothing but maximum independent set. So maximal independent set, there exists independent set. Easy. So if you have referred the class notes, you can easily answer all these things. G contains at least k into k minus 1 by 2 edges. Okay, let me take the same example and verify. Pentagon, number of edges are 5, and option C is at least k into k minus 1 by 2 edges. K is chromatic number, so chromatic number is 3. So is edge greater than equal to this thing? Edge we have found manually 5, chromatic number was 3, so we have calculated, it is coming out as 3. Okay, so 5 is greater than equal to 3, makes sense, so this is true. Yes, G contains at least k into k minus 1 by 2 edges. So C is also true. What about D? G contains a vertex of degree at least k. No, which means this simply says there exists vertex. Contains a vertex means there exists a vertex of degree at least k. So degree greater than equal to k. Check this example, everyone is 2, but chromatic number was 3. So we cannot see, right, that 2 is greater than equal to 3. Can we see? Vertex degree greater than equal to chromatic number, 2 greater than equal to 3. Can we see? No. No. Therefore, this is false. Okay. So D was false, C was true, B was true, A was false. Take that pentagon example and every question can be solved. You can even take different examples to verify. No problem. And you will arrive at the same conclusion. B, C is correct. And that's it for today. I hope you enjoyed the class.